We don't. Not. May I have your attention, please? We're starting our program in about a minute. We should start, right? Good morning, ladies and gentlemen. It's my pleasure to welcome you back here this morning in the Energy Storage Forum. I'm Serena Musa, the MC for those who didn't know me the past 2 days of the event. This forum looks to explore the growing role of grid scale of energy storage in enabling effective utilization of renewable energy resources to achieve the region's objectives toward a sustainable and decarbonized power sector. Through these 3 days, event global experts, industry leaders in the power sector discussed the various challenges associated with planning, deployment, and operation of energy storage technologies. This event also aims to offer a unique opportunity to network with key technology providers, utility leaders, and industry experts who are driving energy storage development and implementation in the Middle East region and globally. Thank you all for being part of this event. I would like to remind you, whoever missed the past sessions, the past 2 days, you can watch it online on our live streaming on YouTube. At this time, I would like to invite our technical MC, Ben Khan, to come forward and begin the first program. Thank you.
All right, welcome back, everyone. This is the 3rd day of our content today. As I mentioned as we closed yesterday, the agenda today is really going to be focused on what's coming in the future. So we have a really great set of speakers this morning, both before and after the break, so we hope you can stick around till lunchtime. As a reminder, we have the Poll Everywhere app. We really do encourage you to provide your questions and thoughts as we're going through. This really helps us to create a record of what everybody is hoping to find out from the various speakers, and whether or not we can address them today in session. We will be capturing those and incorporating them in the follow-up white paper that will come out of this event. This is really just a kickoff. This is an opportunity to bring us together so that we can start to set forward on a plan to bring energy storage in a big way to this region. Great, so without further delay, I'd like to introduce the first session moderator, Neva Espinoza. Please come up to the stage. Neva is our Vice President at EPRI of Generation and Low Carbon Resources, and she will be introducing the next session, the keynote for today's agenda. Neva?
Great, thank you, Ben, and so happy to be here and see you all today. So the past 2 days, we've really spent focused on what I would call more the short term. The next 10 years, how are we going to implement energy storage technologies to achieve our pathways moving forward? So I thought I'd take just a few minutes this morning to shift our focus a little bit to the longer term, to mid-century, to beyond mid-century, 2050, 2060, and bring us back to what we're ultimately trying to achieve on our energy system, which is really a clean energy transition. And when we think about a clean energy transition, and this goes back to some of the framing we talked about on day one, we think about the different pathways it takes in order to get there, and how energy storage plays a role, or maybe doesn't play a role, in all of those different pieces. Starting with energy efficiency. Energy efficiency is critical to this overall decarbonization pathway because it is going to reduce the amount of energy we need per GDP. Reducing the amount of energy we need per GDP is going to become increasingly more important, especially when it comes to energy storage, when you think about the two aspects of this energy transition. And the two aspects I want to focus on is an economy-wide perspective, not just an electric perspective, an entire economy perspective, and the scale it's going to take to actually achieve this. Energy efficiency. Next is decarbonizing the electric sector, reducing carbon intensity. Obviously, energy storage is going to be a huge part of that, much of that being the grid-integrated battery storage that we've been focused on primarily the past 2 days. As we see the integration of renewables, as we can see more variable generation, there's no doubt that batteries are going to have a core role. The third piece, efficient electrification. Efficient electrification and utilizing cleaner electricity to decarbonize other sectors of the economy is going to create significant growth of the overall electric system, requiring more and more energy storage as we move forward. And then beyond that, those three things alone, energy efficiency, a net zero electric sector, and efficient electrification, will not be enough to achieve net zero, period. Will not be enough. Something else is absolutely needed in order for us to achieve the last 20%, 10%, 5%, it'll be different based on region, to achieve net zero. And that's where we bring in this idea of a low carbon fuel. We talked a little bit about hydrogen yesterday, we'll talk a little bit more about that today, as a potential energy storage possibility as we move forward. So when we think about this overall picture, we think about what does our energy economy look like? And today, our energy economy is actually pretty simple. When you think about how do we move energy and how do we carry energy across our energy system to support the entire economy, there's kind of three key ways. The first is what we've been talking about, electricity. Electricity is one of our primary energy carriers here around the world. Electricity represents about 20% of final energy worldwide. The other two pieces are gaseous fuels and liquid fuels. Come in different varieties based on where you are in the world, but gaseous fuels and liquid fuels provide 80% of the world's economy. So when we think about what this energy system looks like moving forward, and we think about moving away from carbon-based energy supply, moving away from hydrocarbons, and replacing it with something else, this whole entire energy system looks a whole lot more complex. Because when you think about energy carriers inherently, when you think about liquid and gaseous fuels, are also energy storage mechanisms, right? We store energy in liquid and gaseous fuels, and we use them at the end use. However, electricity inherently in itself is not an energy storage mechanism, right? Electricity is just an energy carrier. So as we shift to an economy that is more dependent on electricity and shifts maybe further away from liquid and gaseous fuels, we need to find a way to continue to store energy over time, over space, very, very differently than we do today. And what that's going to do is add a whole lot of complexity within our energy system. So when you look at this slide, I like to tell people it's meant to give you a headache. So if you're looking at it and trying to follow the lines, do not do that. That is not what it's meant to do. But what it's meant to do is to give you a feel for how complex our energy system will be as we move forward. a lot more reliant on electricity, a lot more interdependent, where one energy carrier, one energy system interacts with another in a very, very different way. So these one-line diagrams give you a feel for what that may look like, but we thought it would be interesting to show you some of what we've been focused on here at EPRI around what does that mean for maybe the US economy, and how do these energy flows move, and how will this change how we think about energy storage today, and how we should be planning for energy storage tomorrow. So if you look at the energy flows within the United States right now, and this is just one example. It'll be very different from region to region around the world, but they're going to fundamentally be similar in different ways. So on the left-hand side of the slide, you see primary energy, right? Where is energy coming from? And there's kind of three core nodes in the middle. First node's electricity, that's up top. And what do you see going into electricity? It's very similar to what you see in different parts of the world. You see a little bit of renewables. Depending on where you are, you see a chunk of nuclear, maybe 20% or so. You see coal, in this case. And then you also see, in this case, natural gas, which is coming out of pipeline gas, the second node. Right? The second node is basically gaseous fuels. So the second node goes up, creates electricity, and where is that electricity going? Well, today, electricity is primarily going to buildings. A little bit to industry, of course, right? Now, what do you see below that? You see a whole lot of orange. Orange is hydrocarbons, right? So you see a bunch of gaseous fuels, and you see a bunch of petroleum going into liquid fuels. And that is what is supporting the US economy today, right? And it's supporting it across the different end-use sectors. Not unsimilar to what you see around the world. So EPRI has a pretty comprehensive economy-wide model that we look at understanding how will this change over time, this energy economy. And it doesn't just model the electric sector, it models the electric sector, it models the different parts of the economy. It also models all of the other pieces, right? What is going to happen with natural gas? What's going to happen with coal? What is low carbon fuels? How do those all integrate together in order for us to achieve various scenarios as we move forward? So part of one of the studies we did was looking at how can we achieve net zero as an economy as economically as possible. And as with all models, there's a million different scenarios you can go through. I've chosen to put up here and share with you guys a scenario that is really focused on zero carbon, right? There's different ways to achieve net zero. One way to achieve net zero is to be able to sequester carbon, then remove it, so you can have positive emissions, negative emissions, and hit net zero. Another way to hit net zero is to basically significantly reduce the amount of hydrocarbons we use and shift more to a fully green economy. In that scenario, in a scenario where you are not able to sequester carbon for whatever that reason may be, this picture changes significantly. So pay attention to how much role we have in electricity up top. Pay attention to how much orange is there now. Now, 2050, hitting net zero, fully green, if you will. Electricity is made up solely of renewables and nuclear, essentially. It is now, basically, final energy's gone from 20% to around 60% overall final energy of the system. You see electricity now going significantly, of course, to industry, buildings, transportation, across the board. And you see this big blue chunk of electricity, it kind of goes like that, it looks like a snake. That's going to create hydrogen. Hydrogen then goes for many different things, derivative products, synthetic fuels, creating a new mechanism for energy storage. So when you're thinking about grid-scale energy storage and how we're going to design how much energy storage needs to be in our system at the end of the day, without having this economy-wide perspective of how we truly hit these aggressive goals, without understanding the scale of what it's going to take, the amount of electricity needed in this system, the amount of storage needed in this system is easily 10x what we're planning for today for 2030. The capacity on the grid in this scenario is 5 times the installed capacity in the United States right now. So the innovation that is needed, the economy-wide perspective that's needed, and the scale that's needed is significant. So with that, we'll explore some of those things today, lots of different ways to get there. I'm really excited to bring up here Frank Bernard. Frank is the Director of Flexibility at NEOM, and today he's going to be representing the Long Duration Energy Storage Council to share with us a little bit of their perspective on what they're doing and their modeling work. Frank, it's a pleasure to have you.
Thank you. Assalamu alaikum wa rahmatullahi wa barakatuh. Good morning to everyone. I'm very happy to be there. Thank you to GCCIA and to EPRI for this invitation. First of all, I will explain why I'm here. That would make sense if it works. Yeah. So we'll speak about long duration energy storage, and as a director for flexibility and carbon within NEOM, we are also a member, anchor member of an initiative that is called Long Duration Energy Storage Council that came from COP last year, and different organizations decided to join themselves to promote long duration energy storage. So first of all, maybe NEOM, you know, a little more than the ad on Sheikh Zayed Road. It's not an idea, NEOM. It's a reality now. It's a region in Saudi Arabia, part of Vision 2030 of the kingdom. And we have three pillars: green, sustainable, reliable, and also attracting a new economy in this region. And I'm part of the team that take care of the energy needs for the region. And we are also recently organizing differently a bit our structure with an integrated utility that used to be called NEOM Energy and Water and is now named Enova. So I don't know if you've seen that in the press recently. And I welcome you to speak directly to me or go on our website to know a little bit more about ourselves. But I'm not there today for NEOM. I'm there for Long Duration Energy Storage Council. So if you have some question about NEOM, we can take them by the side. So first of all, last year, some leading companies decided to join, as I mentioned, and we have already more than 50 people, 50 entities joining us for these initiatives. So the target is to, as never said before, I mean, green energy, it's wonderful, but the problem is that we absolutely need tools to make it also reliable and covering all the needs of our energy system. And energy storage is fundamental. Energy storage is great also, and so far I think we could have seen that the last 10, 15 years, great for the short-term needs, but we also have long-term needs. And the integration of renewable up to 100%, like for example in NEOM, we absolutely need also long-duration energy storage. And that's the reason why all these companies join forces, so with people who need it for their own system or for their project, for the development project, with equipment suppliers, with startup technology providers, and big consumers. So what are we covering? It's very ambitious. It's very ambitious because we need, in fact, to take care of all the value chain. So it's also international, and we will see that there's maybe some regional focus, but it's with the international reach that was the base of these initiatives. And there's also fundamental subject linked to the specific application for long duration energy storage. So first of all, we have workshop and work streams on 24/7 renewable PPA, how we can make renewable PPA firm and be able to answer to all needs of the customers. We have net zero islands, how you are resilient within the island without fossil fuel. A very, very ambitious subject. Net zero mining also, not only resilience, but it's close to the island, is how also in a difficult location, for example, you can bring 100% renewable without using fossil fuel. The transmission and distribution optimization, it's a very interesting subject because most of the time, one of the big tools for integration of renewable has been the grid. But what is interesting is that grid also need to be supported. And one way to support the grid is energy storage. You can support it on the short term, but you can also support it on the mid-long term. It can be a tool also to help to scale up, because we need also more grid for integration of renewable, and sometimes there's a bit of a discrepancy between the rhythm for which you go ahead with your grid and the rhythm of the operators producing energy, renewable energy. Regulatory, of course, fundamental. You always need to understand which framework you are speaking about and which type of market design can be the optimal to make sure that you have a fair integration of renewable and storage, especially in this case storage, in your system. I personally spend a lot of time on this subject in Europe, and it's critical. It could really be a big bottleneck, but it also can be a huge boost. I've seen that, for example, in UK. Net zero heat, very interesting because we are not speaking only about electricity. Long-term, long-duration energy storage include also something that is not only electricity, and heat is a fundamental subject. Finally, and very interesting and important for LGES Council member is innovation. We are looking at financing some specific project where innovation is needed, where we need to push a little bit more. And for that, I think you've seen before the list of our members. There's a lot of startup, and it's very, very important that we focused on this innovation and investment on this innovation project. And finally, as I mentioned, some specific regional approach. So today, and I'm already late, it's maybe my French style, so sorry I speak too much. But today, one of the part of the plan that the Council had for me today for you was to present you a study that has been made recently that you can find on the link you will see there. So take your time to read it. I think it's a very, very good insight on the impact of long-duration energy storage. So here you have an interesting curve showing the way that you need to integrate duration with, the link between duration and integration of renewable. It looks a little bit self-explaining. I mean, as much renewable you need, more flexibility you need. Of course, the capacity plays also a role, but the deep energy duration is a fundamental one. And for that, you need to put some figures on it, and you need to explain for your market design, for your plan, industrial plan, for your strategy. You need to have a vision on that, and that was a bit of the purpose of this approach. So here we speak about power. So heat and other part will not be treated today. So what is important? Cost. Okay, it's wonderful to speak about technology. It's wonderful to speak about green but if it's not sustainable and viable financially, it will never work. And the reason why renewable are so successful recently is because the cost came down, because it became much more meaningful and viable. So we went through this first report now in much more detail, and the way that it has been structured. So it's very heavy in his approach at the beginning. It's quite serious approach based on, I would say, 3 layers. The first one that is the input from different sources, that most of them are available. So McKinsey supported LDES Council for this purpose. And typically what was the final goal is to estimate the cost of long-duration energy storage and the way to reduce this cost in the future and give a bit of a vision about it. The model used is a McKinsey model that is a model used by maybe some of you in your energy planning. And the output give us the possibility to calculate leverage LDES and LCOS. I will come there a little bit more. So we look at the fundamental now is that what long-duration energy storage is bringing. First of all, and within NEOM, it's one of our priority, load shifting. Okay, what do you do with excess solar during the day and deficit of load during the night? You absolutely need to find solutions for this load shifting. You also have some problems with climate change, is extreme events. What are you doing when during 1 week you have incredible rain in a period of time where you should have not rain at all and sun? You need to find a solution. Also linked potentially to climate change, but also on a structural basis, is what do you do for seasonal issues and imbalance of your system? On top of what I think has been spoke already for the last 2 days, much more on a short-term storage issues and applications like ancillary services that you know already. So here is what I was speaking about, this energy shifting. It's what, with my colleagues, we call the camel curve. We want to stop to speak about the American duck curve, and we focus on the camel curve. Grid service, and also we spoke about optimization of transmission and all the subjects that I mentioned earlier. Which type of long-duration energy storage are we speaking about? It's often a question that LDES Council had, is that what are you promoting? Okay, we promote no one and everyone. So everyone is welcome. At the moment, it's true that lithium-ion has a bit of a kind of a star role, and I think it's good also to show that energy storage is not only lithium-ion. It's great, it's important, but it's not only that. You have plenty of other ones. You have mechanical, hydropump storage that, for example, we are looking at in NEOM. Gravity, compressed air energy storage that we are also looking at in NEOM. Chemical, of course, hydrogen that you heard a lot, I guess, during these days. Electrochemical, so lithium-ion, but not only. You have plenty of other very brilliant ideas on batteries and other type of batteries. And finally, thermal with a CSP, for example. So I think I will run out of time. So this slide is very important because it will summarize a bit of the numbers that you have to keep in mind and a bit of the result of this study. Long-duration energy storage is a big stuff. If you have responsibility as investor, if you have responsibility as industrial, if you have responsibility as a public domain, look at this. It will be really, really, really big. It will support the more integration of renewable in your system. It will be big in terms of capacity we're speaking about several terawatt, not terawatt hour, terawatt is capacity. The amount of money, it's 3 trillion US dollar on top of the renewable energy economy. So less positive is investment return rate. Okay, we should do better. But the interest rates are low, so, you know, we are working on it, and I think it's also interesting, again, to focus on the cost reduction and remember what people were saying about the investment return for renewable 15 or 20 years ago. Everything changed if we scale it up. And to scale it up, we need to give ourselves the means for that. So after that, we have a lot of other slides that may, I would say, confirm the numbers I just showed here. So this one is a little special because it's linked to the cost and the capacity that we will need. I will go maybe focusing on this one, that is concept. You all know the LCOE. There's an LCOS. This formula is a bit, I would say, maybe the most simple and consensual one. So typically what you need to do is very simple, is you add your CapEx, your OpEx, the lifetime, and you divide it by the throughput. So you can refine it, and for storage you need to, because you have different level of application that will request maybe much more complicated calculation. I don't like to compare this because, you know, I mean, sometimes renewable generation people said, oh yes, you said that my job is simple and on your side the storage is complicated. But unfortunately it's true. You know, generation with renewable, it's relatively simple. Storage is much more complicated because you have optionality value. And optionality value is very difficult to calculate it, especially when your electric system not based on a market design that is focused on market price. So if you have a single buyer, like in our case, for example, in NEOM, it's very complicated to calculate and estimate, but we need to. And we need to find a way to go to the first step, and the LCOS is one of them. So in terms of duration, what is long and what is short? The boundaries are moving. You know, I think 10 years ago you would have asked me, okay, in storage, what is short? I would have told you it's 30 minutes. Now I would tell you it's maybe 2 hours of even maybe 4 hours in some specific case like US. The boundaries are changing because the technology is moving also. But typically for us on a LDS council, we are thinking that beyond 6-8 hours, we are speaking about long duration. So on the cost, I really advise you to go much more into details in our study. And here you have a wonderful complicated graph to show you that it's complicated to do storage. That justify my salary. And I think much more interesting for all of you is the market size. So again, it's terawatt we are speaking about. So it's a really, really big stuff coming after renewable energy. Okay, that's the same subject. So here we try to make a bit of difference by region. What I think is interesting is to see that finally everyone is concerned. All economies are concerned. Of course, their integration of renewable will be a bit different, with a different path, with different tools, with different type of needs. But it's, again, the message, I think you all understood it because I repeat it at least 10 times, it's big. Interesting subject, especially, unfortunately, linked to the international situation. The competitiveness of long-duration energy storage is very much linked to the cost of fossil fuel too. So with what's going on the gas side at the moment, long-duration energy storage make even more sense than it used to be only 1 year ago. So of course this model has been, the result of this study has been done a bit a while. You know, if we stay for a while in a difficult international situation, think about this, renewable is at your home and long-duration energy storage is at your home. So it reduces your exposure to external crises. That's the message here. And I'm off in terms of time. So, yeah, again, this is very interesting for the investment return. And here I am.
Wonderful. Thank you, Frank. Great job. So we only have a few minutes here for question and answer, but I would definitely encourage you to, I think they'll throw the barcode up here, the QR code. Please feel free to drop in any questions in the chat, and I will be monitoring them as we have a few minutes. But Frank, so the Long Duration Energy Storage Council announced during COP, I believe, correct? And you know, more than 50 organizations have come together to really focus on these different types of technologies. And you talked a little bit about the importance of innovation. So can you share with us a little bit how the council itself is going to bring together all these collaborative organizations and really push for the innovation we see needed in industry?
Yeah, I mentioned it very briefly, but it's a very, very important subject for LDES Council, and that's the same for NEOM. I mean, we absolutely need to give a chance to innovation, but give a chance to ourselves too, because at the moment when I look at my level, what is available on as technology, I know it's fine, but it may not be enough. And for that, we need to find a way to boost the innovation and the new way to address this long-duration energy storage. At LDES Council, first of all, that the members, you can see that there are some small startups that will share the same working group than big guys like BP or us. You know, so it's already at this level that you have a collaboration. The second level is a financial vehicle that is planned to be set up to finance project, because we've seen also the little problem of IR on the return that this project may have. And we need also a boost there to show that it's possible after that to scale them up.
Absolutely. Absolutely. So any questions here in the audience? Because I have more, and I will keep asking questions for the next couple minutes, but I would welcome anybody in the audience who has some. While they're thinking about that, can you share with us, Frank, so we're all pretty familiar, obviously, with pumped storage hydro, probably our best example of longer duration storage. Obviously, batteries has been a big part of the conversation, but can you give us some of your thoughts on what do you see as some of the upcoming, maybe 2 or 3 long-duration energy storage technologies that you're excited about?
No.
No. He said no. I don't think he's allowed to say that.
No. The reason why I said no is because I will be wrong. You know, I've been so much. I'm more than 20 years in the energy industry. I've been so many times surprised by what happened the last 20 years that now I don't make any forecast anymore. I mean, except when my boss asks it to me because I need for the energy planning. But typically, no, I think yes, there's plenty of things ongoing. I think there's improvement on the battery level, lithium-ion or non-lithium-ion, that's 100% sure. There's interesting things also coming up on gravity, on hydrogen, on different other type of technologies that can apply that we mentioned before. But it's also interesting to see the improvement of the existing long-duration energy storage technology. For example, on hydro pump storage, I mean, in Dubai you have a HATA that will be set up soon. In NEOM, we are looking also at this type of solutions. You can also improve already at the turbine level You can also improve your energy system in terms of efficiency with more digitalization. I mean, there's plenty of ways to integrate that and support a better technologies on long-duration energy storage.
Absolutely. I think the grid integration and the overall system integration is really interesting, and I think we'll talk about that a little later today. But when I look at some of the scale that, I showed a graph, and then you showed some graphs that show scale, the amount of capacity we see in the energy system is, I think you guys had about 4 times what it is today. In your example, I talked about 5 times, yours was in 2040. So how do we scale something like that? What do you see as the biggest challenges, and how do we overcome them for scale?
Yeah, I mean, I think it's to make sure that, the suppliers, the equipment suppliers, and the ecosystem is there. So that I think one of the missions of Long Duration Energy Storage Council is to make sure that everyone is supporting these efforts together. And again, the ecosystem needs all the stakeholders. And if we have that, we can go ahead. At NEOM level, we have exactly the same issue. I mean, we need to make sure that on the regulation, everything is fine, that on the finance, everything is fine, that on the technical, everything is fine. And at our scale, at a region scale, we have exactly the same problem than the other country may have.
Yeah. Early engagement by stakeholders and lots of partnerships across the board, for sure. Well, we are just about out of time for questions. I think I would sum up some of what we heard here on the importance of collaboration as we see through the Long Duration Energy Storage Council and innovation in this space. So with that, Serena, I'll invite you back up to wrap up our session. Thank you so much, everybody.
Thank you, Neva and Frank, for this informative session. And now I would like to invite on stage His Excellency Dr. Naif Al-Abadi, Chairman of GCCIA. Now we're going to present the trophies. Frank Bernard, Director, Flexibility NEOM. Neva Espinoza, Vice President of Energy Supply, EPRI. And now we'll move to the next group photo.
Great, thank you for that great keynote session. I think it helps to see where we're going with these the remaining sessions of the day here. So let's get started with our next session. I'd like to invite up my colleague, Dr. Aidan Toohey, who will moderate this session on planning and other aspects of energy storage. Aidan?
All right. Thank you, Ben, and good morning, all. Yeah, so I'm going to lead off this session on planning and operations with energy storage. We'll have one virtual speaker and 2 in person, and then we'll do the panel discussion at the end. So just before I hand it over to Gabe from California, so I wanted to share some of the recent work we've done with GCCIA on renewable integration, and then kind of what that means and how storage might fit into that. So on the left-hand side, you can see some of the analysis we did last year, where we took the targets and plans for 2030 for each of the member countries and looked at the weather at each spot where potential wind and solar sites might be over multiple years at a 15-minute resolution. And then tried to develop what does that look like. And so I think in the previous session, like the camel curve was mentioned. You can kind of see that here in the very right-hand part of this figure. But basically what we're happening is you're adding a lot of solar and wind onto the system. And that third figure shows that the typical load right now, so the black is the average, and you can see the spread across the year. As you add more solar, you're obviously pushing that down in the middle of the day. And so that kind of resource activity, the way that we've changed how the system operates, is going to have these challenges that we will need to assess. So resource adequacy is one of them. Do we have sufficient resources to meet that middle of the day as well as the peaks and other times of the year? And that's going to change from current planning towards meeting peak summer demand to planning to also have it there during periods when the solar goes down and when there's less flexibility on the system. We do need to be able to balance that. We need to be able to ramp resources up and down throughout the day to manage the solar and wind energy on the system. That's going to mean increasing reserves, increasing need for grid services. We'll need the transmission and distribution or potentially pipelines to support that, to move that energy around and to get an overall more efficient economic system. And then we need to maintain grid stability. So when we do have contingency events on the system, can we make sure that we don't have reliability challenges? All of this, as we're transitioning to that future system, we're going to have to make sure we keep reliability, not just in 2030 or 2040, but every hour of every day between now and 2030 and 2040. So this decarbonised grid needs to have these services, and storage can provide a lot of these, or potentially all of these services. You'll hear from the speakers here the rest of this session. We're going to need to think through which services are most important, which technologies can provide which, and what's overall most economic, and obviously do that at a very regional perspective. It's going to vary in different parts of the world. So with that, I'm going to hand it off to Gabe who's Gabe Murta from California ISO, who's the storage sector manager there at the ISO. We heard yesterday from Elliot Mainzer, the CEO, and he showed us the kind of journey California has been on with getting increased amounts of energy storage, and Gabe is going to talk a bit about how they actually operate and plan that amount of energy storage. So Gabe.
Hey, good morning. It is an honor and a pleasure to be here to be speaking with you today. As you can see from behind me, I'm here in California in the United States, and it is late here, so I'm doing my best to stay awake, but it really is a pleasure to be speaking with you all today about something that I'm very passionate about, which is operating storage resources on the grid here in the state of California, and just thinking about how prevalent these resources are going to be across the entire United States of America, and frankly, the world in the next few years. For years, people have been saying, this revolution where we're going to see a lot of new storage in the system is coming, and I've heard, it's coming. But I have to say that it's finally here in the state of California. So as you heard from the CEO of California ISO, who spoke to you yesterday, the amount of storage that's on our system right now has really grown by leaps and bounds over the last few years. 2 years ago, just for reference, California operates a system that peaks at about 50 gigawatts in the summer. And 2 summers ago, we had about 500 megawatts of installed storage in the system. That's mostly lithium-ion batteries. It doesn't include some older pumped hydro resources that we've had on our system for a long time. Last summer, we had about 1,500 megawatts of storage in the system. Currently today, we have almost 3,000 megawatts of capacity on the system, and we're anticipating that in the next 2 months prior to the summer really kicking off here in California, we're anticipating another 1,000 megawatts. So we've grown by a little bit more, or we're anticipating growing by a little bit more than 3,500 megawatts over the course of about a year and a half. At the same time, the California grid itself is also undergoing some pretty major changes. The state of California has a goal to be generating electricity in a greenhouse gas neutral way by the year 2045. We are making strides in that goal, and that's part of the reason and part of the drive for building and developing so many storage resources today. But at the same time, it's also driving development of new renewable resources, specifically wind and solar. And here in the state of California, solar is typically the more prevalent renewable resource. In addition, the state of California is also making efforts to electrify more sectors of the grid. So they're actively switching, household consumers and businesses from using natural gas for things like heating and cooking to using electricity that would come from the grid to do those same functions in the houses. And part of the new rules that are put in place also require that new homes that are built have electric utilities instead of natural gas utilities. So, this is not only we're not only seeing changes in the makeup of resources that are serving the load, but we're also seeing increases in load as a whole that the ISO needs to serve, which is making our job even more challenging because we have to develop even more resources to be able to address those needs. I just have 2 slides, and I apologize. There are quite a lot of words on these slides, but there's a lot of work that's going on right now in terms of developing storage resources and increasing the power of the tools that we have to model these resources on our grid. And what that's driving is efficient market outcomes where we're really incentivizing the lowest cost resources to provide energy onto our grid. And those are the resources we're accessing and getting energy from, where more expensive resources are being sidelined in favor of least cost resources. So today, the California ISO, and this has been part of my work for several years, has developed tools to model state of charge for storage resources. So we have storage resources on our grid, and we know at any given time what their specific state of charge is for each individual resource. And right now we have 100 plus individual storage resources operating on the grid. And our operators that are working in our control room have visibility not only at the individual resource level, but they also have some information rolled up about specific areas where these resources are located. So in the northern part of our system, in the southern part of the system, in local areas, they can see aggregate amounts of state of charge. This is important to ensure that we can operate the grid, maintain reliability 24/7. We also track this information to ensure that storage resources are never operating above their upper limit or below their lower limit. So for a lot of storage resources, the lower limit would be 0 megawatt hours. For most of the storage resources on the ISO grid, they are 4 hours in duration. So a plus or minus 10 megawatt battery would have 40 megawatt hours of energy charge capability. So they would be operated by the ISO system anywhere between 0 megawatt hours and 40 megawatt hours. We also have modeling that includes round trip efficiencies. So when you charge a storage resource by 10 megawatt hours or put 10 megawatt hours of energy into a storage resource, it's only capable of discharging 8.5 megawatt hours at a later time. And our model includes that information and tracks that for each individual storage resource that's on our grid. And that is an updatable parameter that they can feed into our market software. We're also developing, and this is something that no other ISO or RTO, I don't think in the world does right now, but we're developing this capability for storage resources to bid in not megawatt price pairs, but state of charge or megawatt hour price pairs, which is really an exciting new development. This allows a storage resource to effectively signal to the ISO that, hey, if I'm at a really low level of state of charge, I only want to be dispatched if prices are very high on the system. If, on the other hand, I'm at a pretty high level of state of charge, you can dispatch me even if prices aren't so high. So this is going to be really effective for how our scheduling coordinators for storage resources can bid and operate and optimize their resources in our market. Storage resources are allowed to qualify for ancillary services, and when we had very low penetrations of storage resources, this is primarily what we saw them doing. Now that we have higher and deeper penetrations, we see storage resources primarily providing energy arbitrage services. So they're buying energy when prices are low, they're selling energy when prices are high. We also have specific checks in place in our market to ensure that storage resources that are scheduled to provide ancillary services have sufficient state of charge to be able to provide that service for a full hour or a 15-minute period if we're looking and examining those resources in the real-time markets. The ISO has functionality to exceptionally dispatch and hold storage resources at a particular state of charge. So sometimes we need energy within local areas where we're not able to get enough energy in through transmission lines into a local area to serve load within that area. So sometimes in order to prepare for a situation where we might be expecting an outage, we will pre-position resources to be available within that local area. This could potentially include storage resources, and our operators have the ability to tell them to charge up to a certain level of state of charge and hold that state of charge for a particular amount of time. Similarly, this might not be used for local considerations. This might be used for system considerations as well. We might know that there's a particularly, this is a particularly challenging day. We might have already lost a particular line or another generator on our system. In those cases, we might need to charge specific resources across the grid to make sure they're holding sufficient state of charge that will be able to operate the grid reliably later in the day. Government tax rules, so these are federal government tax rules from the US government that are in place, are causing contracting issues for resources that are participating on our grid where they're not able to fully participate. And specifically, these are resources, storage resources that are located usually with on-site renewable resources, and they have specific contractual obligations that prevents the storage resource from charging when there's not energy coming off of the on-site renewable. So that's something that we're working, it's a challenge for the California grid. It's something that we're working with the federal government to resolve, to try to come up with a better solution so that we can have more broad participation from the storage fleet, which we really need to do, particularly on very hot, very high load days. So if we move to the next slide, please. I was asked just to say a couple words about resource adequacy. There really is a lot to think about here, but I think the most critical component is the second bullet, where not only do we need to consider the amount of capacity that we have from resources, which we've done in the resource adequacy framework in the state of California for years and years, which basically amounts to adding up the total nameplate capacity of the resource, all of the resources of the system, and comparing that to the peak load that we think we're going to need to serve during the year. And if we have enough capacity, which traditionally has been from natural gas burning resources, then we're able to serve load not only during that highest peak time of the year, but also the rest of the 12 months of the year as well. That entire paradigm is shifting, and it's shifting very rapidly. So as we build out more storage resources, the thing we need to keep in mind is storage resources don't actually generate any energy. All they do is they shift it from one time of the day or one time of the week or one time of the year to a different time of the day or time of the week or time of the year. And they do have those inefficiencies that I was talking about before, where you charge a certain amount of energy and you have a little bit less than that amount of energy later to use. We're also depending more and more on renewable resources on our system as we decarbonize, which means that we're more dependent on these resources that could potentially have variable outputs. On days when there's high cloud cover, or here in the state of California, we have wildfires frequently during the summer, and those wildfires can generate smoke, and that smoke can prevent generation of electricity from our solar fleet. So more and more in the future, as we go forward, not only are we going to have to study the peak system conditions when we think loads are going to be the worst, but we might also have to consider multi-day scenarios where we have day after day, or potentially multi-week scenarios where we have conditions that prevent us from producing our full output from our solar resources or our full output from our wind resources because of potentially slack wind conditions, and which could reduce the amount of energy we have, which means we may need to call on not just 4-hour duration storage, but long duration storage to sort of tie us over through these times when we don't have much solar and much wind generation. So there is a lot to think about when we start getting into the topic of resource adequacy and making sure we can operate our grid reliably. And that's something that the ISO and the state of California and frankly others around the country and around the world are sort of grappling with right now. But with that, I think I'll pause, and I'm very excited to get into the discussion part of this, where I can answer some specific questions.
Thanks, Gabe. Yes. Do stick around for the panel discussion. Hope you can stay awake that long. So the next presenter is Dr. Najib Dandashi, who's the CEO of Al Usul, and he's going to talk about some of the issues here in this region.
Okay. Thank you, Aidan. Assalamu alaikum. Thank you for the GCCIA for the invitation. Thank you for EPRI for the invitation. I am honored to be part of this prestigious event with all the experts around here and colleagues from the GCC and beyond. I will try during my presentation not to repeat some of the so many brilliant ideas that we've heard during the last couple of days, but bear with me. I will hopefully approach the issue of the planning and the operation maybe from a different perspective. First of all, I will try to say that the objective is about the power system planning and the operation, and we will see what are the major trends and needs which are driving the sector and in the current and the future landscape, while taking into consideration the various aspects in the context of every single organization. So hopefully that will be also addressed from perhaps more practical point of view, and maybe with some reference to a few countries here in the GCC, just to put things into more perspective. The big picture, obviously, we hear about the looking top-down, climate change, urbanizations, and the increase of demand, the liberalization and technology. They're all together. Every now and then we hear about those, pushing the 3Ds, basically, the decarbonization, decentralization, and digitization of the key industries. Sometimes we hear the 4D, the democratization also. Okay. Basically, this is changing the core of the power sector, and indeed the supporting and the corporate functions. So it's not only the disturbance to the core of the electricity supply industry, electricity and water in this part of the world. Obviously, we cannot separate them, although we're trying to separate them. And disturbing also the structure of the support, for example, through the blockchain, the energy as a service, the electric transportation. And it was mentioned during the last couple of days also, the issue of the electrification of the transportation sector. And it's interesting to see that some of the big giant oil and gas companies are finding that their major customer, which is the transportation sector, is running away from them into the electrification. So what are they doing? Strategically, they're following that customer into the electricity, and as if they are adopting, if you can't beat them, join them. So we can see those big giant oil and gas moving into the electrification. All this is influencing, is making a difference as far as the power sector is concerned. So what is on the world's mind? The Sustainability Development Goals. We are more concerned with 3 of these goals in this forum here: the clean water and the clean energy, and of course Industry 4, which is the digitization effectively. Those 3 sustainability development goals are influencing and shifting and pushing and disturbing the electricity and water sector. Right? So, but are these showstoppers? Certainly not. There are numerous challenges as far as the planning and operation of the power sector is concerned. But these are not showstoppers, and the fact that some countries in the world, they've managed to, for some hours maybe, okay, run their whole system on renewable energy or on zero carbon, means that somebody is doing something right somewhere. So all this is tribute, of course, to the planners and the operators of the power sectors who are keeping everything running and keeping the light on. So they are not showstoppers, challenges certainly, but they're manageable. Everybody put the duck curve, so I thought, yeah, why not? What the hell? I'll put the duck curve as well. But if you look at the duck curve, on the left-hand side on the pickup, it's not a big deal. If you are from a system operation background, you'll see that these are manageables because the pickup in those 3 hours is doable, especially in a big system with large resources. Okay, and those who are aware of the system in the UK, for example, or worked in the UK, they know that the TV pickup is much larger than this pickup during the early hours of the day. So it's manageable. The TV pickup between, you know, at the break of football matches or interruption of, you know, some nice soap opera. So these are doable. And while at the end of the day, the 12.7 gigawatt in 3 hours, that's challenging, but also, so far, it seems that it's doable. So the scaremongering against the renewable energy should not be really allowed to prevail. These are manageables, and it can be with the appropriate resources, of course, and support and proper planning and operation of the system, it can be managed very well, as we can see in this case. Right. Now, this is another interesting curve. This is probably the extreme, okay? And we've seen the camel curve, we've seen the duck curve. I think now let's vote on what kind of animal will fit in this, this curve. This is an extreme scenario of the solar eclipse, taken here from the GCC, obviously. We see and we hear about the intermittency and the variability in terms of the solar energy and the renewable energy in general. And we can see that also from system operation point of view, we're talking about 830 to 1100 hours in the morning, loss of around 400 megawatt, which is 50% roughly of that solar power plant. And this time is doable. So it's not a problem that the variability dropped down the solar output of this power plant, okay? And the intermittency, as well as the variability, which is the extreme in this case here, it's predictable, or it can be forecasted. And in that case, it can be very well planned, operationally planned, and controlled in the control time scale. Okay, I sympathize with the operators, especially those who are here among us today, but this is also not a showstopper. It can be managed with or without storage, especially with a system like the system that we're talking about the systems that we're talking about here in this part of the world. So this is an extreme scenario of the variability, while again, they're predictable, so they're not surprised, and there is sufficient time for the system operator to use available resources, planned resources on the grid, nationally or regionally, to cater for such behavior. Okay, so, but if we look at the planning and the operation process and try to see how the storage, whether that storage is battery storage or hydrogen or any kind of storage, what is required in this planning and operation process? The planning and operation is concerned with addressing the steady state supply requirement, okay, so that's on the generation side, address the grid short-term capacity needs, and allow for optimal energy capacity planning, okay? So it's about the generation, it's about the transmission, it's about the cost. The bottom line is to ensure there is an optimal energy management, optimal grid management in planning and in operation time scale, secure and reliable, securely and reliably. What is also required, perhaps in the storage, is to push back against the renewable energy skeptics. And those renewable energy skeptics are, for example, the people who came out after the incident on the 9th of August in the UK 2019 and immediately pointed the finger at the wind farm that, you know, was part of that incident, that renewable energy, the problem with renewable energy caused this interruption. The same thing happened in Texas when the storm last year, I think it was in February, immediately the first, you know, reports and claims that the weathering of the, or lack of weathering of those plants caused this interruption, and people started to, you know, blame the renewable energy for the failure in the power system, which is not correct. Okay, so what are the evolving needs now? Again, going back to the objective of the power system. But the question is, which power system? Okay, before 1990, the time when Margaret Thatcher and the UK started the privatization, it was the engineer who was running the sector. Planning, designing, and everything, all the influence, all the structuring was by the engineers. Come the privatization, the economists came on board. So the economists joined the engineer in trying to manage the electricity sector and other utilities also. And recently now, relatively recently, we have the environmentalists. So the 3Ds that we talked about are now joined by 3Es. The 3Ds and the 3Es are together, you know, influencing the direction, the sector, the technology, and almost everything else. But the problem is those economists, respectfully, and the environmentalists are dictating in a way sometimes and maybe imposing on the engineers the direction where the sector is going in terms of configuration, structure, planning and operation, maybe. And there are numerous examples that we can discuss and talk about. So the poor engineers now is having to cope and react to what is being done in order to cater for what the economists and the environmentalists are pushing for. When we say what power sector, again, these are animals. I have no ducks or camels here, but there is no one size fit all, and there are differences in the power sectors. Not like previously when the power sector was almost the same, okay? And you look at the grid code, for example, you see the process is very well structured, very well articulated, everything is the same, but now the power sectors are the same, and we cannot claim there is one size that fit all. What do we mean by that? There is an institutional issue, issues to be considered, whether the sector is vertically integrated, whether it's unbundled, whether there is a market setup already in place, and how the storage will factor into the market trading. There is the ancillary services, we've heard about that, and there are some regional opportunities, whether the the utility is interconnected or is not interconnected. And let me here give a quick example about 3 of the countries in the GCC region here, and I take liberty to mention those countries because in certain capacity I'm involved in the sectors and helping with structuring, regulating, reforming. If we take the case of Saudi Arabia, for example, Saudi Arabia has one of the largest renewable energy program in the world. Yeah. And probably, in my opinion, is the largest, and it's the most ambitious. Why is that? Talking about 27 gigawatt in a few years in volume and time, this is to some extent unprecedented, okay? Other countries, they've managed this kind of renewable, but over a longer period of time. Additionally, when we look at the power system, this almost 50% is in the summer, not in the winter. And the problem is going to be in winter, not in the summer, contrary to what people think. It's the winter, the weakness of the system. So quickly, without spending too much time on explaining the background to this, the point is any storage to be, installed for Saudi Arabia, the objective, for example, for Saudi Arabia, in my opinion, the storage should be related to the inertia of the system that will be depleted in a country where you have large industrial load separate from the main grid. You have new development. We've heard about NEOM, about Red Sea, about Alaya, and others. So there are segregated resources while the main system is pushing towards the renewable energy. Oman.
Finish up.
Yeah. Oman is one of my favorite, to be honest. Why? It's very forward-looking, progressive, liberalized. There is a market now in place where the generators bid in the pool to buy and the consumers to sell electricity. And in the same time, there are issues related to the ancillary services, reactive support, and what have you. So all those combinations, it's one of the most forward-looking in the MENA region. They have a system that will allow more players to come and participate. So the requirement for a place like Oman is probably more on the price management, not the adequacy of the capacity. It's price management and inertia because of the impact of the renewable and the impact of the system on the inertia, which is also weakened to some extent, similar to Saudi Arabia. 1 minute?
Yeah, even.
Yeah. I will finish quickly with United Arab Emirates. The system is different here. 4 nuclear units. Each one is roughly, as we've heard yesterday, around 10% of the system, okay? There are batteries, 108 megawatt batteries installed back in 2008. I was privileged to be part of that decision, but the world was different at that time. These were done for system adequacy, not for the support. Right now, taking into consideration of the nuclear, of the solar in Abu Dhabi and in Dubai, the system does not require storage for adequacy, capacity adequacy, requires storage for voltage support, for loss of, for inertia, for synthetic inertia, because the loss of 1,400 megawatt in one go will not cause active power problem. It will cause frequency and voltage stability problem. This is the requirement of the UAE. Last point, I want to take the GCC perspective. Point that was raised by Dr. Nasser in the very beginning, day 1, session 1. Yes, the interconnection is a virtual battery, and it should be leveraged to ensure that this system adequacy can be provided by the GCC interconnection, while other services from the batteries in terms of voltage or stability support can be maybe pursued in a different way in every system, and perhaps on every node of the GCC interconnection nodes or substations. I'm sorry if I've taken more time than I should. There are lots of stories to share with you, but consideration for the time. I'm sorry.
Thank you very much, Jim. Appreciate it. Thank you. And yeah, if you stay up here for the panel discussion. So our last speaker here in the panel is Dr. Salem Al-Hajraf, who's the founder and CEO of Adama Consulting, and give his view in the area.
Thank you. You told me there is a pointer here, but there is nothing. Assalamu alaikum, good morning. It is a great pleasure for me to stand before you this morning and to talk about practical experience we built over the last decade in Kuwait in the field of renewable energy in general and in energy storage specifically. Today I'll talk about the role of energy storage on stabilizing demand-based power supply curve. This is the outline. I will just skip it to save some time. Everybody talk about sustainability and trying to put the strategies and plans to achieve some kind of sustainability. I believe sustainability sit on three key pillars: resource security, economic diversification, and protection of environment. We are in the big top sphere today. Resources, we mean water, food, energy, and raw materials. And this is the resources. Of course, energy is a key over all these resources. The motivation of sustainability mainly came from five drivers: energy scarcity, volatility of oil prices, climate change, and global warming. Of course, without the top three, we can have also population growth and economic growth. Even without the top three, still we have to have the sustainability equation valid. Going back to this morning, we mentioned energy efficiency and how we can consider it as the low-hanging fruit, especially to reduce the per capita high consumption of Kuwait, UAE, Qatar, Saudi Arabia, Bahrain, and Oman. You can see the average world is down there, the Europe average is here, and the GCC average is up there. So these big circles need to be reduced. To start with, we have to think about energy efficiency at most. Then we think about all others as a complement to that. Again, camel curve. Thank you, Frank, for introducing us to this curve. This is a typical demand curve in all GCC countries. And this is the Kuwait curve. You can see from January, February, March, it is called the low demand curve, and also December can be added to them, the winter month. The moment we turn on our air conditioning systems, the curve starts going up. In Kuwait, we produced about 66 terawatt hour in 2020 from about 20 gigawatt installed capacity. Of course, we are not using all of it because we are expecting about 100,000 residential units to be commissioned over the next 5 years, and this buffer zone was reserved for these new cities. But again, the peak load reached around June, July, and August, and this is where we have to focus our attention, since we have less than 50% of our installed capacity utilized as a base load. The rest is to cover the high demand. Also, when we think about renewable and energy storage, we should look at this solar energy, global solar radiation. In 1 year, we have 8,760 hours. These hours, half of it, the zeros, are the night. And the colored one are the daylight when the sun is up. So if you focus on the red zone, this is the zone where we can harvest solar, both to direct generation of electricity or to charge our energy storage systems. Back to the curve. As I said, the base load can be produced, and grid operators and plant operators love to stay in this zone because it is systematic and flat production. Oil, gas, coal, nuclear, and hydro are best fit for base load. For the curve up or the peak demand curves, we can have solar thermal, solar PV, wind, energy storage, and other renewable technologies. But as you see, the blue zone is the waste or underutilized capacity installed. It stays off until we reach that curve. Renewable energy can be used for power shaving, and this is what we are practicing right now in Kuwait. Back in 2010, we started developing the master plan of what we called the Shagaya Renewable Energy Park. I was privileged to initiate and develop this project until commissioning in 2018. The Shagaya project separated into 3 phases. Phase 1, which I led 70 megawatt PV pilot, consists of 10 megawatt wind turbine, 10 megawatt PV, and 50 megawatt CSB plant with 8 hours energy storage, thermal energy storage capabilities. This is the plant immediately after commercial operation day. The big solar field, in fact, it is our boiler. We replaced the boiler, the fuel boiler, with the big solar field. It is 50 megawatt CSP plant. We designed it to be zero fuel burning. It is 100% solar power plant with zero burning fuel. 8 to 10 hours energy storage capabilities, and of course it can work 24 hours, 7 days a week because of the energy storage. I will show you some real graphs of that, and also it is commissioned since 2018. This is during the design phase. In 2012, we set and start to study the strategy we should follow. The first curve here is the CSB without the green one, without energy storage. This curve, if we add 4 to 8 hours storage, this curve, if we add 8 to 10 hours storage, and the orange one, if we add 10 to 16 hours storage, this can cover the short night we have during summer and the long day we utilize to run and charge also our energy storage. This is this curve from last summer. This is a daily life cycle of our plant. You can see the apparatus, normal isolation. The yellow curve is the solar radiation. The red or purple curve shows the thermal energy storage curve. It charged from sunrise to sunset. Then at the moment when sunset reached about hour 18, we shift to the energy storage. So we kept the solar plant, the solar thermal plant running till the end of the day and the beginning of the following day without shutting down the plant. Here is the average, or not the average, the actual data from 2020. And you can see the contribution of energy storage in every month's total power evacuated to the grid. You can see the contribution became high during summer months and a little bit low during winter months because the solar system cannot be charged fully. Now let us see how can we utilize hydrogen as an additional tool for energy storage. Of course, we can use PV, wind, and surplus grid electricity to produce green hydrogen, but also we can use the thermal storage or the thermal energy we collected to generate or produce blue hydrogen from hydrocarbons. Of course, thermal energy storage can be used for the daily cycle. We charge it during the day and discharge during the night, so we cannot store it for a seasonal period. But for hydrogen, we can generate hydrogen in the green zone. It is green with blue slashes, so that we can generate blue and green hydrogen during off-peak or during winter months, so that we can use hydrogen as a seasonal storage while using solar thermal or even battery for a daily cyclic storage so that we can resolve a big portion of the peak demand we're facing every summer in the GCC countries. This is my last slide, and it is hypothetical and probably a dream that one day we can better utilize the oil fields. The oil fields in Kuwait or in the GCC countries or everywhere in the world, usually it is in the remote areas. It is underutilized because we are extracting the energy from about 4,000 meters under the ground without utilizing the surface of the desert. So if we move solar thermal plants around the solar field, we can extract oil as a hydrocarbon. Then from the thermal energy we collected from the sun, we can extract the hydrogen from the hydrocarbons and sequestrate the carbon back to the oil field so that we can export clean energy from the oil field, from the source. And from my point of view, this will be the most optimum way to handle or for oil-producing countries to keep a firm stand on the future energy market and to keep our market share. We should follow a strategy either similar to this or closer to this so that we can convert our oil fields to be a green fields where we can produce both hydrocarbons and clean fuel from the source. And of course, sequestrate carbon on the site. And this is from my side, and thank you for listening, and I'm looking for your questions. Hopefully we can answer it.
Okay, thank you, Dr. Salam. So while we're seeing if there's any questions from the audience, I do want to start, and hopefully Gabe is back on and can be brought up on the screen here when we get a chance. I did want to start with Gabe, and obviously California has already been implementing quite a few of the energy storage systems. And so one of the things I know that's a big issue on that is around energy charge or storage state of charge management, and whether or not the ISO needs to know that. There's been a lot of discussion on that in the industry in the US. So Gabe, any experience around how you studied the need for what data you need to get from the storage plant, how you verify it, and other aspects like that?
Yeah, can you hear me?
Yep.
Great, okay. Yeah, ensuring that our markets know what the state of charge is for storage resources is critical for their operation. For example, our day-ahead markets that we run in the state of California, it's a 24-hour market. It's got 24 one-hour segments, and each of those segments is optimized over the entire time horizon. So we look at, all the graphs that we're showing on the screens where we see, low loads during the middle part of the day, high loads during the evening. Our markets see all 24 hours, and they inherently know that the best times to charge the storage resources are when prices are low, and the times that we're going to be discharging the resources are when prices are high, and that's going to maximize the economic efficiency of our market solution. So what we're effectively doing is charging the resources when marginal costs are relatively low, sometimes with marginal renewable energy. So our solar's generating a lot of energy, and that's what's charging the storage resources. And then during the later times of the day in the evening, we're offsetting much more expensive, sometimes peaking gas or natural gas resources on our system. But you can't do any of that if you don't know what the state of charge is of the resources, because you have to know, how much energy to put into the resources in the first place, how much energy that you could potentially discharge from your resources. And then it's important that your operations team, who's actually monitoring this in real time, knows that information as well, because if there is a loss of one particular element or an issue in a local area, they may need to charge the resource up And to do that, they would need to know what state of charge the resource actually has. So here in California, we have two different ways of sort of getting that information. The first is through our market model, where we are tracking the dispatch instructions, the 5-minute to 5-minute instructions of where we are sending that resource. Are we telling them to charge? Are we telling them to discharge? And that information gets incorporated in what we're forecasting the state of charge to be. And then we also get telemetered information directly from the resource that gets sent to the ISO. That happens on a 10-second basis. And we can use that information to verify where that state of charge actually is compared to where we thought it was, and then we can update that information intermittently. But it's incredibly important to have this. If you're using a model to determine dispatch instructions for your resources, it's important that this information is included in the model.
Okay, thanks, Gabe. For this region, as you look to California and see what's happening there, and we'll hear in a while about the UK, what are the types of things you're watching for in energy storage? Obviously, it's a different regulatory structure here, different market structure, but what are their experiences that you think are going to be most important for us to learn from in this region?
If I start with the UAE, for example, as I said earlier, the started initiative in storage in the UAE was purely for VVIP and capacity supply security. 2008, it was like contracted for 300 megawatt at that time. Okay, although we installed 108, and it was part of that decision, make no apology about that. It was specifically for the capacity security. It was a different world then. So it's not really appropriate for me to say now that it was not the right decision in 2008 when we are talking now about a different world. Nowadays, the world is more concerned, and the region here should be more concerned with the reliability, with the resilience, with the inertia, lack of inertia, with the voltage stability, not the capacity security. That will not be covered if we lose 1,400 megawatt for the nuclear, for example. And the institutional side, when you have the system operator moved away from the transmission business into the procurer, almost like a system operator, independent system operator, don't know if it is still independent, but the planning and operation process now is fragmented. So that added to the complexity and to the worry of the system operator. The point is, need to look into every single institutional context and accordingly find what is required to give the value stream from that storage and which storage.
Yeah.
From my side, I don't think there is one technology can resolve all the problems. It is an optimization exercise. And the optimization is site-specific and market-specific. So what is applicable for Saudi Arabia probably is not applicable for UAE or Kuwait and so on. So we have to be localized when we search for a solution. What bother grid operators is the stability of the grid, especially with renewable. For example, if we are going to design 1.5 gigawatt PV, the grid operator will ask us to provide a spinning reserve to cover up in case of dust storm or in case of cloud cover. For spinning reserve, in Kuwait, we agree with Ministry of Electricity to allocate 500 megawatt spinning reserve from gas turbine. When we said spinning reserve, we mean a turbine running on the idle, but it consumes gas. The moment we run out of solar, for example, immediately we can shift to the gas turbine. This is, in fact, a costly solution. In order to expand the build and development of PV projects within GCC, we have to think about energy storage as a spinning reserve at the first period. And later, after that, we can think about energy storage as a source of energy, where we can send the power plant, especially the thermal or PV, in any remote area in the desert where water is available, so we can produce either green hydrogen or blue hydrogen. Then we transport it to the power stations so that we can inject it to the grid as electrons.
Okay, yeah, that's interesting. And I know we're running out of time here, so I'm just going to maybe have a final question for Gabe there. So, Gabe, I guess I was going to ask what keeps you up at night, but I think that's presenting to conferences at the other side of the world. But what does, in terms of where you're seeing things go, what are your big thing? Maybe we'll have to be pretty quick here, but what's your big kind of concern at the moment?
The absolute biggest concern for me is resource adequacy. So, we've been operating in the US and particularly here in California with a system that's been overbuilt for years. So there really hasn't been any problem with us being able to meet loads during any time of the day, no matter what the circumstances are. That paradigm is rapidly shifting, where we are retiring older gas resources, taking those resources that can generate 24/7 off of the system and replacing them with renewable resources and storage resources is an extremely challenging task. And at the same time, we've got increasing or expected increasing loads across the state. And frankly, I think we could very easily see ourselves in a situation where, the lights do go out, and the first organization to get blamed is the ISO. ISO, why do you let this happen? And that means that we really need to double down on our efforts to ensure that we do have enough resources to ensure reliability on the grid. But that's an ongoing struggle because the higher the bar is for resources that you need, the more costly it is to get there. And obviously that's a key consideration for ratepayers.
All right. Thanks, Gabe. Well, unfortunately, that's all the time we have. So appreciate the panelists, and thank you, everyone.
Thank you.
I think we'll stay on stage for a second. Really.
Thanks to all our speakers. And now we would like to invite on stage His Excellency Engineer Ahmed Al-Ibrahim, CEO of GCCIA, to present trophies to the speakers. Dr. Aiden Touhi, Program Manager of Grid Operation and Planning, EPRI. Dr. Najib Dahmani, CEO of Al Asul. Dr. Salem Al-Hajraf, founder and CEO of Idama Consult. Group photo, please. And now I would like to remind our attendees once again to follow GCCIA social media platforms to stay with the latest updates of the event. Also, you can watch the live streaming event on GCCIA YouTube channel. And now we will take a short break for 30 minutes.
No. We're going to go to Julian Leslie from...
Okay, so we will resume the session.
Yeah. So we've one last speaker, Julian Leslie from National Grid ESO will be joining us again virtually. So hopefully we can get Julian up on the screen. So National Grid ESO is the independent system operator for the UK, and with their decarbonisation policies and goals, they have very aggressive targets for operating a low carbon grid, and Julian will talk about the role storage has to play in that. So a lot of really good work going on there, a lot of good demonstration projects that can be used to kind of understand how we can use these types of resources on the system. So waiting for Julian to come up, but we're good. Yeah. For those who haven't been familiar with what's going on in the UK, they're starting to get to the point where they're looking by 2025 to operate the grid with 100% clean energy resources. That's mostly renewable inverter-based resources. As an island system, that gives them a lot of challenges in terms of the way they have to operate the system, with a lot more inverter-based resources, a lot of the wind up in the north of the country. So a lot of interesting challenges there in store for the UK. Now we got Julian on? Yeah, there we are. Yeah. So Julian.
Good morning, Aidan. Good morning, everybody. Morning. Can you hear me?
Yes.
Great. Well, thank you for the introduction. It's a great pleasure to be talking to you this morning. Sorry I can't be there in person. I would love to be there, but logistics just didn't work out. So I'm Julian Leslie. I'm Head of Networks and Chief Engineer for the System Operator here in Great Britain. And as Aidan said, I'm just going to talk through some of the high-level principles and activities that we're working through now. We're really focusing on the role of storage and how that's making a difference as to how we think about and plan and operate the future electricity grid here in Great Britain. So we'll just go to the first slide, please. So I'm just going to give a quick summary of what we mean by that zero carbon operation that Aidan's just been mentioning. Understanding the role of storage in allowing us to do that. Then there's a few slides at the end just for Great Britain is to talk about actually the scale of the storage that's required and what are those future challenges and how that's being progressed here in Britain. So next slide, please. So what do we mean by zero carbon operation? So here in Great Britain, we've had a tremendous sort of success in decarbonisation over the last 10 years or so, with a sort of over 70% reduction in our carbon emissions over the last 10 years. And coal really plays a very, very small part in how we operate the grid, with sort of 1% of our energy coming from coal last year, which is a tremendous success. However, we want to go further than that. We want to be able to also run the system without the gas that we currently have. And there are times now when the market in Great Britain on a low demand day that's sunny and windy, the market would deliver us a zero carbon power solution. So nuclear, wind, solar, and a bit of hydro. And in today's world, we need to then take action in the market in order to constrain off renewable generation, in order to bring on gas, because we need inertia, frequency response, voltage control, etc. But what we hope to be able to do, or what we will do by 2025, so just 3 years from now, is that we will have procured enough products and services which are zero carbon, which means that when the market delivers us a zero carbon solution, we will not have to interfere in the market and we will be able to operate the grid at zero carbon. You know, we expect in 2025, this will only be for a few short periods throughout the year, but obviously that will grow over time. And our Prime Minister made a commitment before COP26 that the energy system, or the electricity system in Great Britain, will be 100% fossil fuel free 100% of the time. So that is our challenge. Now you can see there's some records there. So last May, or well, actually 2 years ago, in May, we had 85% zero carbon. Now we know exactly what the 15% non-zero carbon, what it was and why it was procured to run on the system. So we are looking to find zero carbon ways to replace that 15% that we bought for services. And then we had a record just a few weeks ago where we had 66% of all of our energy needs were provided by wind on January the 29th. So you can really see how we are progressing over time and how we are getting close to that magic moment in 2025 where we'll be able to run the system with 100% at zero carbon. Next slide, please. So what are we doing to enable this to happen? And then we'll get into how storage is playing a role in this. So as Aidan said, we run these things called pathfinders. This is a sort of regulatory sandbox, you might want to call it. It's an opportunity for us through pathfinders to work out what are the technical and regulatory and commercial challenges that need to be resolved in order to provide zero carbon solutions to the services that we need. So we've ran 4 or 5 various pathfinders now looking to buy voltage control at zero carbon, but most excitingly, and I guess the world leading piece is buying inertia or short circuit in-feed at zero carbon also. So stability, as you know, and as the previous speakers were saying, as we decarbonize the grid system, we lose that rotating mass of the large fossil fuel conventional power generation being replaced with power electronics. And that could cause, without address, it would cause stability issues on the grid system. So what we are doing through our stability pathfinder is that we're procuring these zero carbon solutions. So far they've ranged from spinning a hydro plant, spinning it in air or in water at 0 megawatts. We've had conversion of an old CCGT, a gas-fired power station, that has sort of taken the generation aspect off, and it just spins in synchronicity with the network, providing the mass. And then we've also commissioned just the other week a machine from General Electric, which is designed specifically to provide rotating mass on the system. So it's a very small motor, effectively, again, 0 megawatts, 0 carbon, but it's 250 tons in weight. So it provides a huge amount of inertia for a very small device. So that's sort of some of the innovation that's coming. The new innovation that's going to come for phase 2 on stability is that here in the UK, we've defined what a grid forming inverter needs to do and how you technically design a grid forming inverter. Now, with that grid forming inverter on a battery or a solar farm or a wind farm, then it means, or it turns that renewable inverter-based resource into something which looks and feels like a conventional power plant. So you can get inertia, you can get short circuit in feed, you can get frequency response and voltage control and black start services if you put a grid forming inverter onto your storage device or your renewable device. So that's really exciting, and they'll be on the system. There's a wind farm on the system today which has grid forming inverters and behaves just like a conventional power plant. And then by 2024, we will have a bunch of storage devices which will also provide similar services using that grid forming inverters. As many of you in the audience will know, that trade-off between inertia and frequency response is a trade-off. The more inertia you have, then the longer your frequency response can take. The lighter your inertia, then the quicker your frequency response needs to be. So we introduced just over a year ago something called dynamic containment, which again is a service that's designed really well for batteries, and batteries perform really well in the space. And what this is doing is looking at the frequency on the system. It has a bit of a dead band around 50 hertz. We operate a 50 hertz system. And as the frequency falls or rises above a certain threshold, then these batteries deliver the full energy output or full energy input in order to manage frequency. But the important thing here is that it does all of that within a second. So because it's doing it within a second, it's delivering that energy into the system within a second, and therefore it catches the fall in frequency and allows us to run a much lighter system with regards to inertia. When you think previously our primary and secondary response was sort of to be delivered within 10 seconds and sustainable for a couple of minutes, what batteries have allowed us to do is to get that response within a second, and it's maintained for an hour or 2 hours, however the size of the battery is. So it's really changed the way we think about frequency management and inertia on the system. But because of that, though, we are able to withstand a greater rate of change of frequency, to be able to catch the frequency and return it back to normal. But we had over 15 gigawatts of capacity on the distributed energy resources, which had an old style rate of change of frequency setting. So we've had to go around It says here nearly 9,000 sites. It's more than that now. It's more like 15,000 sites where we've had to change the protection settings so we can run the system much lighter with a much greater rate of change of frequency. And that's what delivers the best value for the consumers. As you look at system restoration, again, as I said already, we have a wind farm with a battery, which can provide black start services. But also we're looking at how do you build the system back up using the distributed resources, so using the distributed storage and wind and solar, and how do you rebuild the system from the bottom up, whereas historically in a black start situation, you would start at the transmission level and then sort of build across the transmission network and then go down to distribution networks. And we're looking at how you do that the other way around. Next slide, please. So I guess the key purpose of today is to talk about storage. So some of this I've covered already, but we see that storage has a huge role to play, and it's so flexible that it can play in many, many markets and provide many, many services that the system needs. Frequency I've talked about quite a bit, so delivering power within a second allows us to run the system much lighter with much less inertia. So that's a really strong, we've got over 1 gigawatt of dynamic containment provided by batteries in our markets. Stability, we don't have any of these on the system yet, but we are about to procure 7 or 8 different sites with batteries and grid forming inverters, which provide short circuit in-feed in Scotland, and they'll be on the system within the next 2 years, so April 2024. Again, what we're seeing is that the innovation that's coming through for our voltage management, that storage with a rotating synchronous generator. So again, you've got the rotating mass, your synchronous compensator, your synchronous generator, combined with the battery, again, can provide great voltage support, as well as providing that inertia and frequency response also. One thing we've explored on the thermal, so this is where there's a thermal constraint on the system, we've explored, can you get a virtual transmission line with a storage device, one side of the exporting constraint, which is importing, and then another storage device on the other side of the export constraint, which is exporting, and therefore the two are working in concert with each other and creating this virtual power line. So we think there's something really exciting there. What the challenge is today with our network and the amount of constraints that we've got is that the size and the scale of that storage would have to be huge, and there isn't the technologies yet in those locations that can make that happen. But it's something that we're absolutely open to, and something where two storage devices can really have a role to play there to create this virtual transmission line. And then restoration, as talked about already, we've got this wind farm in Scotland that is capable of doing that already. As we look to the future though, and we get more and more renewables, the flexibility and adequacy are the two new things we really need to think about. So flexibility, sort of the within day or the within a couple of days, to move the load on the system really to match the generation that we have on when the sun is up or the wind is blowing, and then match that with the peak sort of underlying load of the consumer load on the system. And having storage to move that peak from when it gets dark in GB to actually the peak might be in the afternoon, because that's when it's most windy and most sunny. So the storage should fill at that point. And then when people come home from work and they start cooking their tea and their heating comes on in their homes, then actually the energy is coming from the storage devices across the grid rather than the renewable resources. Then if you look to adequacy though, so how do we ensure that if we have a period of very cold weather with not a lot of wind, or in the summer we have got a long period with not a lot of sun and not a lot of wind, where do we get our energy from? And that's the big conundrum. It's the one thing that does keep me awake at night, is how do we ensure that reliability of supply through long periods of low renewable output? And I'll come on to some of that in a moment. So next slide, please. So the GB electricity system is currently it's a winter peaking system at about 50 gigawatts. And mainly that load is lighting and domestic heating in the winter. But if you look at the amount of storage that we need on the system, you can see there our future energy scenarios are sort of looking at the gigawatts of installed capacity sort of by 2050, anywhere in the region of 20 gigawatts of storage up to 40 gigawatts of storage, which is a huge amount. When you think today we've probably got 3 or 4 gigawatts of storage on the system playing in the different services and embedded in distribution networks. This is a huge, huge, huge increase in storage devices. But if you look at, well, what is going to provide that long-term storage, if you're moving away from the battery technology, then we believe that hydrogen is going to be a key fuel that helps us on this transition. And you can see on the right-hand side there, the scale of that storage of capacity of that hydrogen storage could be anything up to 50 terawatt hours by 2050 in one of our scenarios. So that's, again, it's a huge amount of energy, which will be using the excess renewable energy from the electricity system to create the hydrogen. But the big challenge there is, well, A, how do we get that scale of hydrogen electrolysis on the system? And B, where do you store 50 terawatt hours of hydrogen? And how do you store it? And that's some of the key challenges that we're facing. Next slide, please. We've done some analysis for 2035, so just sort of 15, 16 years from now. And we will have the two extremes here. On the left-hand side is where the demand on the dotted yellow line is well above the generation sources on the system. And then on the right-hand side, you can see the opposite, where actually the generation sources are well above the dotted yellow line, which is the demand required on the system. Obviously, on the right-hand side, that's where storage could be filling and is soaking up that excess generation. But on the left-hand side, obviously, there's a shortfall. So what form of storage is going to fill that huge volume of gap between the colours, the generation, and that dotted yellow line? Next slide, please. So if you look at the profile of generation and demand across the year, the purple and the orange circle you can see on the screen, those are the two scenarios that were on the previous slide. You can see from this slide there's a lot of time in 2035, where in all years actually, where the generation, so below the x-axis, where the generation is in excess of demand. So we've got plenty of opportunity to store energy, and there is enough energy around on the system. The big challenge is, where do we store that energy? How do we store it? How long do we need to store it for? And in what form is it going to be stored? And what are the market arrangements to make that happen? So our government has recognised this as an issue, and they launched a consultation at the back end of last summer, asking the industry as to what would it need in terms of subsidy or regulatory frameworks in order to bring these storage devices to the market. And we're still waiting what the outcome of that will be. Although I think it will be something around a cap and floor regime like we have for our interconnectors with our neighbouring countries here in Great Britain. Next slide, please. And this is just sort of showing you the changes through the year. So the blue line on the graph there is sort of the hydrogen storage daily stock levels in 2050. So you can see that by the time we get to the end of our winter, that we've used pretty much all of the hydrogen that's in store. But then we spend the summer when the renewable output is still going to be relatively high, but the demand is falling away. We use the summer to store and create hydrogen and store it away. Then you can see as we get into the winter months, sort of September, October time, you can see that we start to then use that hydrogen that's stored over time to meet the peak demands over the winter, and then we go back through that cycle again. The big question, of course, is, well, this might be fine for a normal winter, but what happens when you get an extreme winter? How do you know what that extreme winter is going to do? How do you know when it's going to happen? Do you build a lot more storage just for something that's going to happen once every 20 years or once every 15 years or whatever? How do you make that investment case? How do you ensure the market stores that energy in there and keeps it in there, keeping it that 1 in 20 year sort of extreme weather event to ensure a reliability of supply? And that's one of the big questions. Next slide, please. So hopefully that's been a quick canter through what we are doing here in Great Britain and how storage is playing a crucial role in decarbonising the network. If you want to know more about what are we doing and how we're going to get to there, there's 5 publications you can see on the screen, all of which are available on our website. And each of these has very useful insights. Some of them are quite technical, some of them are very readable, and it covers both the market angle but also the technical angles as well as to what we need to do to get to this zero carbon system by 2025, but then more importantly now, how we get to 100% fossil fuel free by 2035, which, as you all know, working in this industry, 10 to 12 years is not a long time at all to make this sort of transformation. So I think that's my last slide. So thank you all very much for listening, and thank you for giving me the opportunity to speak to you all this morning. Aidan, back to you.
Thanks, Julian. So we do have time for a few questions. I see there's one down here, and maybe as the microphone's going down, I just want to ask you something, Julian. So you've done those demonstration products, the Pathfinders, and I know there was, I guess it was an actual product, enhanced frequency response with storage a few years ago. Was there any surprises or lessons learned that you had there, or if not, what were the kind of planning studies you had done to make sure you didn't have those kind of surprises?
So I think, our approach in Britain has been to really define clearly the technical needs that we are looking for. So we're not defining the solution, we're defining the need. And then what we do, we allow the market then to sort of say, well, if that is what the performance that you need full output within a second or whatever, then the market brings forward its recommendation and its solution and bids a price into the market for that. Obviously, we do that technical assessment to make sure that what the developer is telling us that their product can do, we model it to make sure that it can. But I think it takes a lot of the risk away from the system operator by defining clearly what is the outcome of the service, and then we allow the market then to deliver that outcome, rather than me having to then define what that technical service should be and how they should configure their network and their systems. We let the market do that, and then we measure and ensure that the output that they say they're going to deliver is what they deliver.
Okay, thanks. Yeah, we had a question down here.
Thanks, Julian, for your excellent presentation. I'm Kosala from Sri Lanka Energy, USA Sri Lanka Energy Program. I have 2 questions. One is that depending on the role of the storage, can you assign a price tag for that, depending on the role that it provides? The second thing is that I know that there was an initiative where the EV batteries could be act as a spinning reserve. There were some initiatives and thinking that has been, any updates on that? Those were my 2 questions. Thank you.
Okay, so on the first question, it's a pure market. So we define what services are consistent with each other, so you can stack your revenue streams, and we define which services actually you can't. If you're providing one particular service, then that excludes you from providing another. But we run very open and transparent markets here in Britain, so the developers bid in a price that they think is going to be successful for whatever their costs are, and then we sort of go down a price stack and we just we procure the amount that we need at the lowest cost for consumers. So their cost is really driven by the markets and what the participants want to enter into that. The second question, I didn't quite capture all of it, but it's the frequency response. It is with the batteries, it's the speed of their response that they can provide. Yeah, we are looking at, I think it was to do with EVs, that was the question. So we are looking at how do you aggregate that, those batteries in the cars, and how do you get all of that coming together all at the same time?
Sure.
So I think that was that the question.
Yeah, it was whether the vehicle batteries, when it plugged in, also can act as spinning reserve, or maybe that can be given to back any benefits that the utilities derive out of that can be given back to these car owners.
Sure. So I mean, it wouldn't be spinning reserve because obviously it's not spinning, but can it provide frequency response? Then yes, and that's what we're working with now with aggregators to understand the timing, because it's, as I said earlier, the speed at which you can get a frequency response onto the system means you can run a much lighter and lower inertia system. Obviously, with cars, with all the communications involved, it's got to spot the frequency response. It's then got to work out that something has happened. It's then got to communicate with 10 million electric vehicles. The vehicles then need to decide what to do. Then they start putting their energy back into the system. My gut feel is all of that just takes too long. Whereas your directly connected battery, it's in the market, it's monitoring the frequency, it sees a frequency go, within a second it delivers full output. Because you've got far less communications involved in that process.
Yeah, thanks, Julian.
Because the alternative is you've got a frequency response monitor on every car across the nation, which is going to be really expensive. Sorry, Aid.
No, thanks, Julian. We've time for one last question.
Yes, thank you, Frank Wouters. I'm with Gore Street Capital and Reliance Industries. I have one question. I didn't see much of demand response in your forward projections. Is there a specific reason for that? Maybe I've missed it?
No, so I mean, demand response is a key role, and it's what they call demand response or flexibility. So flexibility is absolutely something which is critical and crucial. We are working now with various suppliers across Great Britain, so Octopus Energy, for example. They have flexible tariffs for their consumers, and people are being paid now to charge their vehicle on a windy Sunday afternoon when the demand is low and the wind is high. Then Octopus will pay their customers to charge their vehicle. So that is something, that's the beginning of something which is going to be huge. We're going to have 10 million electric vehicles on the roads by 2030 here in Great Britain. So this is an example of where they must be smart in the way that they charge. We must have that flexibility in order to move the times as to when those cars are charging or not. And then as we electrify people's homes, then similarly again, we need that control and that demand side flexibility. So it absolutely is a two-sided thing. It's the generation and it's the demand. And I keep saying to my control room, say, look, you dispatch generation to meet demand today. I think by 2030, we'll be dispatching demand to meet the generation, because now is the generation is a thing you can't control, and the demand is the thing you can control, because you've got storage, you've got EVs, you've got electric heating. So it absolutely will flip on its head at some point in the next 5 to 10 years, and we'll be dispatching much more demand to meet the generation.
Absolutely. All right, well, we're out of time for the session, so thank you again, Julian, and appreciate your input. Thanks.
Thank you, Dr. Aidan Tuhi, for moderating this session. Thank you, Julian, Leslie, for the wonderful remarks. Our appreciation to the remote speakers who participated in this event remotely. Now we will take a short break for about 30 minutes, and we will resume back at 11:30. Please be on time so that we can start the next session in 30 minutes. we're starting our next session in about a minute.
All right, welcome back from break, everyone. So happy to have you here. You are here for the final, penultimate session of the conference. We're going to be focusing on the technologies now, emerging energy storage technologies. To start, I'll introduce the session moderator. We can invite him up to the stage. Mr. Ben Cowan, Program Manager of the EPRI Energy Storage Program. Thank you very much. I'll come back, okay. All right. So, I'll step over here. So just a reminder once again, if you have questions, please put them in the Poll Everywhere app. As I mentioned, we'll be focused on the technologies for this session. So I have a few topics that I just want to go through and frame this up before we bring on our distinguished speakers who are going to take us through some of the individual innovations that they are working on to try to address some of the open gaps for energy storage. So here's me at a much younger age. So I'm going to talk just a little bit about the challenges, the opportunities, and the current state of energy storage technologies. So as we talked about in the opening session way back 2 days ago, there are several categories of energy storage that are being considered with different strengths and weaknesses. They fall into these 5 different categories: electrochemical or batteries, electromechanical, chemical, such as hydrogen and hydrogen carriers, electrical, such as capacitors, and thermal storage systems. A number of these we will be talking about in this session. We have good representation from the different groups. We are not going to be talking about hydrogen specifically or electrical, but we have examples from 3 of the 5 categories in this session. And just another, background slide, just to remind everyone, globally, 90% of all energy storage that has been deployed cumulatively to date is pumped hydro storage. Of the rest, about 7.5% has been electrochemical or batteries, which is the fastest growing segment currently. And within that segment, lithium-ion has been the dominant technology. So I would like to just talk a little bit about these two dominant technologies, because they're really the benchmark at this moment in time that we're measuring all other storage technologies against when we look at the current and future needs of the grid. This was another slide I showed on the first overview day of the various technology differentiators that we're talking about. Just going to quickly go around the wheel here. Safety, environmental and public health, cost, particularly life cycle cost, siting considerations, technology maturity, performance, which can be efficiency, speed and accuracy, deployment timeline, so how long does it take to put a project in the ground, and then life, so how many years or how many cycles does the technology last in commercial operation. So I want to talk about pumped hydro, and then I want to talk about lithium-ion a little more. So pumped hydro is a mature technology. We're very familiar with it. It also has some known limitations, and some of the ones I want to highlight are from the environmental perspective. These are very large projects in many areas of the world due to environmental permitting. These projects can be costly, they can be less flexible than intended because of managing water levels, and they're just major public works projects. Similarly, with siting considerations, you have to have the right geology, topography to be able to create lakes and pump water up and release it through a turbine. And then deployment timeline. These are very large projects. They take several to many years to actually build the dams and get them filled up. So they're not a great solution for a problem that you have now. They require a lot of forethought. When we look at lithium-ion, this is a technology that has certain vulnerabilities as well. One is life. We're not sure exactly how long these systems will last in their commercial applications. Maybe it's 10 years, maybe it's 15, maybe it's 20, but we don't have the track record to prove it at this point in time, and this is quite a bit less than other grid assets. Safety, so lithium-ion is a very energy-dense technology. It also stores a lot of energy in its chemical bonds. It, as a result, can be prone to a phenomenon called thermal runaway, which can result in fires and sometimes explosions. Environmental and public health, we hear more about the supply chain issues associated with energy storage and some of the human and environmental concerns with getting the components. So these are an area of concern, as well as the recyclability. And then finally, life cycle costs, which is related to the lifetime. Lithium-ion is proving to be a very good technology for shorter duration energy storage, but as you go longer, the cost may not be, or may be too high to support some of the really longer duration applications. So I want to talk just a little bit about some modeling that has been done to give a few insights on where these different storage technologies might fit in and where they might be going in the future. In the first session today, our Vice President, Neva Espinoza, provided a little overview of EPRI's regen economy-wide modeling for decarbonization scenarios. There's kind of a lot of content here, but I'll break down what's going on. There were 4 different scenarios that were looked at as we were exploring the role of long-duration energy storage in the future. On the left side, we have 4 segments here. On the left side, we have the reference case, which is really no additional policy. The second slice is net zero, which allows for carbon removal technologies and doesn't necessarily require complete decarbonization of the electric sector. We have a carbon-free scenario, which does require decarbonization of the electric sector entirely, but allows nuclear power, as well as carbon capture and storage. And then we have a renewable-only scenario. And so what we find is that as we go from left to right, it's increasingly restrictive on what how you can plan and operate your power system. In the first scenario, the type of storage that gets chosen is mostly short duration energy storage, which is really dominated by lithium-ion technology. This is a US study, about 25 gigawatts was chosen. Also just mention that there are some other limitations. Really, we're just looking at the bulk electric system here. We're not looking at distributed applications and other things of that nature. In the second scenario, we have a net zero scenario, and in this one, we're seeing more longer duration energy storage into the 4 to 8 hour range, which is dominantly mechanical, and so what ends up happening is it shrinks part of the electrochemical battery slice, but we do have a balance of two. And then in the third scenario, which is carbon-free, now you can see there's a lot more longer duration energy storage, mechanical, 4 to 8 to 30 hours. We have some more thermal pumped heat technologies for 30 to 50 hours, and then hydrogen for 100 hours or more. And then finally, in the most aggressive scenario, renewable-only scenario, we're seeing those longer duration requirements growing even larger. And in that one, actually, the lithium-ion slice disappeared entirely, replaced by a portfolio of other technologies. In that one, though, this one chose 670 gigawatts of storage in the United States, which is over a factor of 10 more than what is currently deployed. So right now, the Department of Energy has recognized that the existing lithium-ion technologies, which are dominant in the market for short-duration technologies, are only going to take the power system so far, and so they've identified what they call an Earthshot initiative to try to reduce the costs of long-duration storage by 90%. And so there's some various technologies that are potentially in play for this, maybe not to get to the full 90%, but it's a goal that's out there, an ambitious goal. And so one of the scenarios we wanted to look at in the regen modeling was to see what would happen if such a hypothetical battery or storage system were created. And so we looked at a technology that was hypothetically $100 a kilowatt on the power side and $35 a kilowatt hour on the energy side, which isn't quite a 10x reduction or a 90% reduction, but it's the way there. And we looked at it from a range of 50% to 75% efficiency just to see what would happen. And what we found was that such a technology does, particularly in the high efficiency case, take over a lot of the needs of a lithium-ion system, as well as compete with some of that intermediate duration mechanical and thermal, but it does not actually exclude these other technologies. So even a 90% reduction in battery costs is still going to result in the need of a portfolio of solutions beyond batteries to get to really deep decarbonization scenarios. And this particular scenario that I'm showing on this slide is the carbon-free scenario, so not the renewables only, but the second most restrictive class. So just wanted to put a couple of additional considerations just for the context we're in. Here in the Gulf states, we have a hot climate, so we need to consider the climate, we'll say resilience of the technology that's in play. Doesn't need to be kept at a room temperature to operate safely, reliably, or efficiently. I also want to acknowledge the aridity or lack of rain. Having said this, I know that there are a number of sites that are still being considered for pumped hydro in the region related to desalination, and that some of the topography exists, but just generally speaking, there's not a lot of rivers flowing to dam up lakes. So with that, that's the end of my opening remarks. Hopefully this provides a little bit of context to bring in some of the individual technology providers and share what they're offering and how it relates to some of these challenges that are currently ongoing with energy storage to meet the future power system needs. So with that, I'd like to invite our first speaker up. Adam Briggs, Chief Commercial Officer from EPRI, who's going to take us through his presentation. There we go.
Awesome. Thank you very much.
Thank you.
And thank you to EPRI and GCC for the invitation. Happy to speak here today. I know this is a bit of a lightning round. We've got 12 minutes to speak, so although I have given this presentation in 3 minutes recently, so 12 minutes actually feels like a reasonably comfortable amount of time. So I'm going to go off the script just a little bit and tell you I'm a career battery person. Started in batteries right out of college, which was almost 40 years ago. And I've seen a lot happen in the battery industry. And so my lens for what's happened over the last 2 days, I'm going to summarize in a little bit of a simplified way here. So I heard from Bruce Smith yesterday that lower cost energy storage is needed for an investable business case for daily arbitrage. From Neva this morning, I heard that efficiency is important for energy storage. From Frank, I heard up to 10 hours of energy storage will get us to 60 to 70% renewable penetration. And from Dr. Najib and from Julian earlier today, I heard the importance of fast-acting resources to balance the grid against sudden, unpredictable events is important. And Ben just told us that lithium-ion and pumped hydro are good, not great. So from a person who's been in the battery world all my life, that's what I've heard out of the last couple of days. And so that's context for me to talk about a new battery system, and a new battery system that solves some of those issues and addresses this energy storage requirement coming forward. So EPRI is a completely new battery chemistry, and it came out of MIT almost 15 years ago and was initially financed by Bill Gates. So Bill Gates was actually taking an online chemistry course from a professor at MIT and anonymously. And so one day, Bill Gates' administrative assistant called the professor's office, said, "I'd like to meet with you because you've talked about this battery system and I'd like to talk about it." And the professor said, I don't talk to anonymous students who are taking my courses online, so tell them thanks, but no thanks. And so the second time his administrative assistant called, she said, "It's Bill Gates. He'd like to talk to you." And he said, the professor said, "Sure, right. I believe that." So the third time she said, "I really think it's Bill Gates," and he ended up financing EPRI. Now, batteries are a tough technology, and it takes a long time to bring them to commercial success. So I'm here to tell you that after 15 years, we're about to enter commercial success. And the battery has really unique features. So first of all, it is less expensive than lithium-ion. So 25 to 50% pricing below lithium-ion on a dollars per kilowatt hour basis. It has a 20-year lifetime with minimal degradation across that. So we see zero degradation, but we do not make our engineers guarantee perfection. So we have a specification of 5% degradation over 20 years on daily usage of this battery. It is a battery system that we have not found a way to make it unsafe. So it does not have a thermal runaway aspect to it. It can be abused. You can do whatever you want to it. It does not have the ability of generating gas inside that cell. So gas leads to pressure, pressure leads to temperature, which leads to pressure, which leads to temperature. That's thermal runaway. This battery chemistry doesn't have that capability. And lastly, it uses completely novel materials. So this is a calcium antimony battery system. So we're not sharing materials with the EV market. We're not sharing it with other battery chemistries out there. So those are the highlights of that battery system, and I'll dig into those a little bit further. So EPRI is recently raised capital from a group of investors you see on the bottom bullet there. So that includes one of the largest companies in India. In addition to Gates, one of the companies, one of the mines in the United States that will produce antimony is owned by John Paulson and Company, so there's a strategic investor there. And the picture you're seeing is a building block of battery systems from this technology. And so this is the battery system. It is a no moving parts cell, similar to lithium-ion. Those cells go into a shipping container, similar to lithium-ion. And that shipping container has a voltage similar to lithium-ion. So it uses the same inverters, same process. The difference is there's no on-site assembly. We manufacture this entire system at a factory. We ship it to a project site. You drop it in just like you do a transformer, and you make external connections, right? No on-site assembly. And as I said, the battery system behaves a lot like lithium-ion. So it is a reasonably high efficiency system. You can see 80 to 90% depending on how you use it. And so what is unique about this battery system is that it's a high temperature system. So similar to what Gauthier was talking about yesterday, the sodium sulfur technology has kind of blazed the trail for high temperature battery systems. This is another one. It is at 500 degrees C. So inside that shipping container, all of that is at 500 degrees C. So there's insulation inside the walls of that container, which contains the heat. So it's the opposite of lithium-ion. Lithium-ion is trying to remove the heat. We're trying to contain it. So that means we have no air conditioning system. We don't care what the outside temperature it is. It can be 100 degrees C outside. It doesn't matter. It also could be minus 100 degrees C. We don't care. So this creates a battery system that has, therefore takes advantage of the fact that it doesn't have any parasitic load. It doesn't require power in order to operate. It makes for a good black start battery because you don't have to operate cooling if the grid goes down. And so EPRI is about ready to commercialize this technology. So in 2 weeks, we are installing our first system, which is for one of the world's largest data center companies. And then in 23, we will be producing from our pilot production facility in the United States, our first pilot systems. And so Ben and I have been talking about an EPRI-involved pilot system in the United States. So these are those containers that you saw being dropped at different locations. Utilities are interested, some developers are interested, and the plan is to sprinkle about 5 or 6 of those around the world in 2023. In 24, we have our first production year in which we make about 200 megawatt hours of these battery systems, and we open our US high volume manufacturing facility in 2024, which then produces about 3 gigawatt hours in 2025, leading to about 15 gigawatt hours in 2030. And as I'll tell you later, we have 3 more international manufacturing plants scheduled to build our production to about 50 gigawatt hours in 2030 around the world. And so just quickly around the technology. So it's a high temperature technology. So that means that, as I said, it has no cooling. It's good for the extremely hot or cold environments around the world. It's the high temperature that enables the use of these materials. So at room temperature, when we make these cells and we assemble the system and we ship it to a site and we install that system, there is no voltage on these batteries. There's no current can flow through them. Only during commissioning, when we operate the heaters inside the system to heat it up, does it then become an operating battery when it reaches its full operating temperature. So that takes about a day to get to that temperature. And then we disconnect those heaters because just like every other battery, when you use it, it generates heat. When you charge it, when you discharge it, it generates heat, just like the battery in my cell phone, which warms up the more we use it. So the insulation captures that heat, keeps the battery at its operating temperature with therefore no other power required. So that means this is a battery made for daily usage. It likes heavy usage. So the more you use it, the more heat it generates. It likes to be hot. So this is a battery made for energy shifting. Every day, twice a day, 3 times a day, shift big blocks of energy. It also is instantaneous power. So you can use it for frequency response or dynamic containment or whatever type of instantaneous power requirements you mean. By instantaneous, I mean 0 to full power in less than a second, just as Julian was talking about in the UK. So that's what got batteries on the market, was fast-acting resource. Now we're looking for long duration. We don't want to give up the attributes that made batteries attractive. So that's important to take into consideration when you're thinking about next generation energy storage systems. And so how we bid on projects. So this is that container I talked about, which is a 10-foot standard container. We can stack them on top of each other because we don't have air conditioning ducts that are typical for lithium ion. So that reduces our footprint. So we will size a project using a building block like this, and then we will lay out a project using those building blocks. So this uses 38 of those 32 megawatt hour building blocks to create a 1.2 gigawatt hour project. So this is an under 2 hectares of space for 1.2 gigawatt hours, which in the desert, maybe space footprint isn't the most important thing, but in a lot of places around the world, land's expensive and it makes a difference. So I talked about safety earlier. So safety is measured by organizations like Underwriters Laboratories. They abuse the battery by short-circuiting it, overcharging it, over-discharging it, and measure whether there's a fire or an explosion. These batteries not only don't have fires or explosion, you can put them right back into usage. They don't get affected by these types of abuse conditions. We haven't found a way to make them abusive. Antimony is a recycled material today. 30% of the antimony in the world, it comes from recycled antimony. So at the end of life of these batteries, extremely easy to separate the antimony and the stainless steel, which is the construction of the cell, from the calcium, which is the third material in there. So calcium dissolves in water, the other things don't. So now you have a positive value at the end of life because antimony and stainless steel go right into the recycling market. And just quickly to talk about the costs, so it's a lower cost of energy because the materials used, antimony and calcium, are lower cost than lithium ions materials, and therefore our costs are about half of the material costs of a lithium ion system. We don't have the cooling. We don't have the degradation that needs to be accounted for in the expense of an energy storage system. So with lower costs at the CapEx level and lower costs at the OpEx level because we do not have a service requirement for this energy storage system. The day you heat it up, you close that door, you operate it every day, it has no service requirements other than that, no moving parts. And just lastly, I've got the join the duck curve family here, so that's what it's intended for, is shifting that energy no matter what your daily requirement is. And last slide, our production plan I referred to earlier. So we are building our first manufacturing plant in the US. We have 3 international plants that we're negotiating joint venture agreements with right now. One of those in the Middle East would be terrific for us. And thanks for your attention, and I appreciate any questions that come out.
Thank you. Thank you, Adam, for taking us through the technology in 15 minutes or less. Next, I would like to invite our next speaker up, Dr. Nastaran Kravchik, the Chief Technology Officer of CM Blue Energy.
Thank you. Okay. Good morning, and thank you, GCCIA and EPRI, for having us here. And I think we heard a lot last few days that energy storage is necessary, low-cost energy storage, and high-efficient energy storage is necessary. And this is what I want to talk about. So I want to present you the battery we developed. It is organic solid flow battery. It's a kind of redox flow battery, and the battery we developed is truly safe. It's a truly sustainable and truly scalable battery. So what does it mean? We have a water-based energy storage. So it's not flammable, it doesn't burn, it doesn't explode, it's not toxic. It's really a safe battery, and we use no critical material. So it's all abundant, low-cost material which we use for our energy storage. And truly scalable, we already heard on the first day and also today from Ben that redox flow batteries are really good scalable. You have the power and the energy completely independent on each other. So you can have 500 megawatts with 500 megawatt hours, or you can have the 500 megawatts with 2,000 or 5,000 megawatt hours. And where are we right now? So we have a technology readiness level of 7 right now, and we want to have the TRL 8 this year. So what does it mean? It means we have already prototypes running, and this year we will start running the prototypes or the demonstrators in a relevant environment, so in the field with the customer. And what is the performance of the battery? We can show that 10,000 cycles are possible. It always depends on the operation mode and the maintenance. And we have a round trip efficiency more than 85%. And this is why I said it's a sort of flow battery. As we already learned, flow batteries are not that efficient. We will see later why we are so efficient. And as I already said, you can have 50-minute storage, you can have 15-hour storage, or even more, whatever you need. And it is possible to have this battery in the megawatt hour and the gigawatt hour range. It's modular, so it depends on the customer needs. And the costs are really highly competitive. It's comparable or competitive with lithium-ion batteries, even in the future. And the huge advantage of our battery is the higher your duration of energy storage, so the more energy you have compared to your power, the lower are the costs. It's not linear, so it's not that you can reach $0 per kilowatt hour, but it's better to have a long duration battery. And how did we develop this and achieve this? We have started actually on a white sheet of paper, and I could tell you maybe an hour or longer the whole story, how it came to the battery, but we don't do this now. Just for orientation, in 2015, I was one of the first employees. We were 3 employees at CM Blue. And now we have more than 100 researchers, and we have a huge lab, or more than one. We have 80, so the slide is old, we have 80 cells running in parallel. These are small research and development cells where we test our own material, which we develop in-house. This means the electrolyte, the energy storage material itself, but also the hardware, the electrodes, the membranes, the frames, everything. And we have 10 tests running in parallel for the original size, where we test the scale-up process, and we have our prototypes running. So we are quite sure one of the largest non-lithium-ion labs worldwide. And since end of 2020, we are also running our own pilot production for this organic solid flow battery. And how is the company structure? The company is completely privately owned. Our founder is also here today, Peter Geigle, and we have really experienced shareholders who are experiencing new technologies in huge companies. And we are located in Alzenau. It's near Frankfurt. We have more than 130 employees. And so I think you can see from this slide, these are the best conditions for the development of a completely new technology. It's a really convenient way to develop such a new technology from a white sheet of paper. And we are really grateful for this. And now, since I have not much time left, I will go very quickly through the technology. So if there are some more questions, because I cannot explain it in detail right now, we can do it afterwards. So the the baseline is that the battery is oriented on, on what nature does for energy storage. So nature has over a billion of years of experience and uses the most effective processes. And in nature, also in our organism, energy storage is always organic. It's not with metals or metal ions, as it is, for example, for oxygen. It's an iron ion. It is for energy storage, it's always organic. And this is what we started with an organic material dissolved in water. This is why I told you this is a really safe battery. And the battery is running like a flow battery. So you have the liquid, which brings you the electrons, but the energy storage, and now this is the difference to the conventional flow battery and why I said we have a sort of flow battery. It's a solid state battery because we store our energy in the solid, in the tank. So you see the squares in the tank. This is a solid material we have on both sides, on negative and positive side, a solid material which stores the energy. So this is a solid state battery, but solid state batteries have a lot of disadvantages because they have volume expansion of the materials and it doesn't fit together, so you have cracks, you lose contact and so on, and we do not have these disadvantages since we have the solid in contact only with the liquid. So the energy storage material, the active material, remains in the tank, has no contact to membrane or electrode, and this is why we have such a huge lifetime. And this solid material has an energy density of 200 watt-hours per liter. So for a usual flow battery, you have 20 watt-hours per liter. For an organic flow battery, you may achieve 30 watt-hours per liter, but this material which we use has already 200 watt-hours per liter. We are working on the next generation with 500 watt-hours per liter. If you do it in theory and you calculate what materials can do, it's more than 1,000, more in the range of 2,000 watt-hours per liter. But right now we have the 200. So we have, as I already told, the huge advantage that the solid material is only in contact with the liquid. And the solid material is a plastic material, it's a polymer, we do it on ourselves, we develop the whole production, and you have more than 90%, actually it's more about 98% of the energy stored in this very cheap and very abundant material. And you have the liquid, you still need it because the liquid brings you the electrons from the electrode to the active material in the tank, but it's only 2% of the whole capacity, so it doesn't matter if it's a little bit more expensive. And you see here on the right side how this solid material looks like. So this is the material, the black pellets you see, which stores 200 watt-hours per liter. It looks on both sides the same because we need to make it somehow conductive with additives. This is why it's always black. So we have a very powerful energy storage material with a very high energy density. It's safe. It's a plastic material, as you know it from daily life. It's stable and it's really cheap. This is the power unit. So to get the electrons out of the material and to use them, you need a power unit. This is a stack, as you know it from other flow batteries or from fuel cells. And you see we have no sealing material. It's a really simple stack design. It's all welded, and the materials we use are all abundant. We have frames. This is standard plastic material, PP. We have our electrodes, which are mainly based on graphite and a little bit of plastic. And we have our membranes, which are not Nephon. They are completely carbon-based, no critical material in there. So the stacks are also very simple, very stable and cheap. And a huge advantage, you can recycle them. It's all plastic and graphite, there is nothing else. And now I want to show you how our demonstrator or how our product looks like. So we start here with the demonstrators. These are test systems you see on the left side. A test system as it looks like what we are running right now in Alzenau near Frankfurt. So you are invited to see it running at our site. You see here two of these power units of the stacks on one pallet with small tanks behind. So for testing, we need less storage duration just to have more cycles in the same time. And you see the electronic up there. So we have a 30-minute battery here on a pallet. And on the right side, you see also a test system, a 2-hour storage system, which we are building right now. So if you visit us in a few weeks, you can see this too. And this is slightly different. So you have a tank pallet, which feeds the power pallet. And depending on the size of this tank pallet, you can adjust the amount of energy storage. So how many hours do you want to store in your battery? And this testing system, as you see it, so it's not really efficient. You see the first and the last pallet are only have only half of the power units, but this is for symmetry reasons because this is an EU project where we will build this battery a second time in September this year in the south of Spain. And the project is about how can you do energy storage working in an environment of 80 degrees. So when the sun is shining in the south of Spain, which battery will be most suitable for this application, and this is what we do there. So it will start in September. Actually, it will be not that warm in September, but we will see then next year in summer how the battery performs. We already did the tests in the lab, so there is no problem with heating the battery during the battery is running. It works even better because chemical reactions are better when the temperature is higher. And what you see here is one project that we are planning right now. You see here a 50 megawatt battery with 200 megawatt hours. And you see the design, what I showed you on the slide before. We have a power unit pallet, tank pallet, power unit pallet alternating. And for this 200 megawatt hours, we need 50 meters by 40 meters. So it's quite small area for the whole energy. And you can have the same battery, the 50 megawatt battery with 600 megawatt hours. You see here, so it's still the 50 meters on the one side, and on the other side, instead of 40 meters, it's 50 meters. The reason is you have 2 tank pallets feeding 1 power pallet. And you see the tank pallets are higher, and this is why you can have 600 megawatt hours on such a small area. Yes, this is what I told you right now in words. So the higher tank pallets feeding 2 tank pallets feeding 1 power pallet. Yes. And my time is over, so it's the last slide. What we achieved is we have developed the technology, and what we are doing right now is validation and certification, and next year we will start commercialization. So this is why we need the TRL 8 this year. And then I think it's a logical way, then globalization, value chain expansion. So what I try to show you is we have a really large-scale energy storage. We can make megawatt hours, gigawatt hours. It depends on the customer requirements. We can scale power and energy independently. And we have a really safe battery which cannot explode. It does not burn. It's really safe. It's recyclable. We have no conflict materials in. And it's really scalable. And there is no problem with high temperature application. Thank you. I think, yes, thank you.
Thank you, Dr. Kropczyk. I would like to invite our next speaker up, where is he? Rembrandt Neeson from Energy Dome, who's going to take us away from electrochemical and in the direction of mechanical and
That's right.
thermal. Here you go.
Good morning, everyone. Afternoon, actually, I think already is over here. And first of all, thank you to the GCCIA and to EPRI for this late invitation to speak. Claudio, the CEO, was meant to be here, but he was called away for a closing on a transaction. So he sent me and said, I'm not an engineer, but you can try all the questions that you want, and I'll do my best. I repeat many of the sentiments that the previous speaker and the one before that had in terms of the need for long-duration energy storage and how it is so very different from lithium. My own background, I've been in energy, renewable energy for 30 years. I started in wind 30 years ago, was very excited then. Today I'm in storage. I'm the Chief Commercial Officer at Energy Dome, and I'm just as excited, if not more so, today than I was 30 years ago, and I'll show you why. We have an energy storage solution that actually is indeed mechanical. It is not chemical. And it stores energy on utility scale as of now. I'm very excited about the technology. I only joined 9 months ago as a CCO, and we will be commissioning our first commercial system as early as next month. But let me take a step back and explain to you a little bit about the company, which is founded by Claudio, the CEO. Claudio and the engineering team have a deep background in new product development, from a white piece of paper to a new product to market to COD to commercial operation. Started a company called Exergy, sold the business, started a company called Sabigas, sold the business, they're both still running. And just 2 years ago, he started this company called Energy Dome, and we have this storage technology where the process is the innovation, but the product is actually off the shelf, as you will see later on. So we all know that the need for storage is driven by renewable energy. I've been in the space for 30 years. I've seen the cost of a kilowatt hour come down from 25 cents to 2.5 cents or even less in the right environment. So the need for storage is obvious. What is less obvious is what kind of storage you need, because the choice of storage actually is not that obvious. Lithium is very good at short duration. Hydrogen is very good at very long duration. But where there is a gap, lack of a solution, and this is, I think, the space that we're all addressing, is the 24-hour challenge, I call it. We address this, like I said, not by a chemical means, but by a mechanical means. I don't know whether any of you looked at our website at all, but we store energy by compressing CO2 from gaseous state to the liquid phase. And similar things have been tried and tested and actually done by other companies when you look at compressed air energy storage and at liquid air energy storage. If we compare the CO2 battery, as we call it, to these other two technologies, is very quickly. If you take, in the case of compressed air, you take a kilo of air, you compress it to 70 bar, and then the volume reduces, as you can see here, to 12 liters, but it has a relatively low energy density, low single digits. So you have a very large volume with small energy, low energy density storage. So you need massive volumes, therefore you need to do it underground, where you have the reservoir, or else you go above ground, and your material costs will just become too high. You need too many air vessels, compressed air vessels. There's another technology which is very similar to it, which is called liquid air energy storage. There's a couple of companies, I won't mention the names here, you probably know them, and they say, well, actually, rather than just compressing it, you want to liquefy it. So they take the same kilo of air, they compress it to 15 bar, and at the same time they chill it to minus 190. And you see that the volume reduces to just over a liter with a very attractive energy density of over 100 kilowatt hours a cubic meter. Very attractive, but, and there are two buts. The but it's in the minus 190. The minus 190 takes a lot of energy to get the air down to minus 190 and even more to keep it there. So you have a significant round-trip efficiency penalty. The second but is also the minus 190. You cannot deal with minus 190 temperatures with normal carbon steel. So the system is relatively expensive. So the brainwave that Claudio had is replacing the air by CO2. And unlike air, CO2 actually goes liquid at ambient temperature at 70 bar. So if you take a kilo of CO2, you compress it like air to 70 bar, then the volume reduces like liquid air to just over a liter with an energy density of 70 kilowatt hours a cubic meter. So it's very similar to liquid air. So you have the advantages of one without the disadvantages of the other. So I have a little animation here. Ram, if you could just press play, please. And then pause it when I say pause, which is about here. Then I'll explain to you how the system works. If you mind, pause it now for a second, just please, Ram. I'll just explain how the system is set up. On the far right, you see the grid interconnect, which in fact is the only interconnection with the outside world, because the totality is a closed loop system. Next to the grid interconnect, you see the dome, which is a large dome that gives the company its name, which holds CO2, industrial grade, atmospheric pressure, ambient temperature. It doesn't matter whether the temperature is minus 20 or plus 20, minus 40 or plus 40, it always works. To the left of that, you see a turbine that drives the generator during discharge. To the left of that, you see the compressor that takes the CO2 from atmospheric to 70 bar. To the left of that, you see a thermal energy store. As you compress CO2 to the volumes that I described, it gives off a lot of heat. You want to store that heat for later use. To the far left, you see then the liquid CO2 vessels, and the water circuit is just for heat management. If you wouldn't mind pressing play, please, Ram. So now we are charging the system. You see that we take power off the grid, which drives the motor, which in turn drives the compressor. The compressor compresses the CO2 to 70 bar. Like I said, it gives off heat. The heat is now stored in the thermal energy store. At this point, the CO2 is at 70 bar, back at ambient temperature. We condense it before we store it in the liquid CO2 vessels. And you see that the dome on the right is now emptying. At this point, the system is fully charged, and if we want to discharge, we simply reverse the process. And we flow the CO2 out of the liquid CO2 tanks. It picks up heat that we stored earlier from the thermal energy store. It now, by force of nature, it has to expand, does so in the turbo expander. The turbo expander drives the generator in the middle. The dome reinflates. Power is going back to the grid. And that's all there is to it. It is so simple, which is why I'm so excited about this. And if this one page is not exciting enough, then I think the other one, the next one, is even more exciting or just as exciting. And what this shows is that, I think I mentioned earlier, Claudio hasn't really invented anything because all of these components are off the shelf. So we don't need to prove new processes. We don't need to prove new components. Everything is off the shelf. The dome, you see a bunch of names here that supply these domes as a matter of routine with performance warranties, by the way. The same holds for the turbine, the same holds for the expander, the same holds for the generator. And the CO2 vessels and the thermal energy store vessels are just that. High-pressure vessel that you can buy from any high-street steelworks, if you will. So the process is new. The components are all proven, tried, and tested. Now, the system is modular. We store in either 100 or 200 megawatt-hour blocks, and we compress at either 25 or 12.5 megawatt. We discharge at 10 or 20 megawatt, and the choice is completely up to the user. You can have a large turbine and a small expander, large turbine, small compressor, large compressor, small turbine. So depending on the use case, you configure the system as you see fit. The system in itself is relatively large because we have the dome. But then again, everything is relative because this is what you see when you want to store the power of a 100 megawatt solar farm into baseload. And you see the footprint is actually relatively small. This is where you see a rendering of the CO2 dome for a 100 megawatt hour system. Let's quickly compare to lithium, though. We are 75% efficient. We have a capex of about half that of lithium, and we get a lifetime of 2 or 3 times. It's 25 years design life without performance degradation, and the capex, like I mentioned, is about half. The capex is about half today. Lithium is coming down over time. It's coming down quite fast. We will come down just as fast, like you can see here. The technology is nearly mature. The top line is meant to be green, but change of color. We actually address anything from a few minutes up to 24 hours. We're rotating equipment, so we provide inertia. We are actually building our demonstrator, and it is commercial scale, if you will. It's 2.5 megawatt, 4 megawatt hours. Will be commissioned next month in Italy. Left top, you see the compressor. Right top, the shiny cylinders are the thermal energy stores, and low at the bottom, you see, of course, what is the dome that holds the CO2. We're very excited about the product. We've already sold a commercial system, 100 megawatt hours, 10 hours of storage. Something about the company timeline. We've had some very positive recent press coverage. You see that Bloomberg selected us as one of the finalists in their new technology competition for zero carbon. We raised 10 million in our Series A. We are about to launch a Series B after the commissioning of the demo. We are now in the region actually talking to some of your fellow region people. The first commercial system might make NTP within this year. When I say commercial system, our standard size really is 20 megawatt times 10 hours. I think that sums it up. Very happy to take questions now or later, and if not, in the break.
Thank you, Rembrandt, for your presentation. And we will have time for questions. So I do want to encourage you that if you have questions for any of the panelists, to please put those into the PolEV app. Once again, that's polev.com/storagedubai, and the QR code is here on the screen. So given the importance of lithium-ion, I would be remiss to talk about the future of lithium-ion in this session. So I'd like to invite up Dr. Samuel Mao of Khalifa University, who's going to take us through some of those innovations. Dr. Mao?
Thank you. Thank you for introduction. Which one? This one?
That's to advance, yes. Is this one?
Okay, I'm Samuel Mao from Khalifa University. I came to first to thank you, the GCCIA and EPRI for the invitation, and I'm really honored. I came to Khalifa University to lead the Mars Institute about 2 years ago from California, from Berkeley. It's really my great honor to be working here to contribute to the growth of the GCC region, in particular the UAE. My first slide, I think everyone knows that for batteries, what do we want? We want better performance, we want low cost, and I put something at the bottom. It is statistics from DOE about 2 years ago that for 466 global grid-scale battery energy storage projects, that 2 years ago, a bit older data, in particular I put there. We noticed that lithium-ion batteries contribute to about more than 60%. Second one is the flow battery, about 13%. And over the past 2 or 3 years, as Bernard already mentioned in his introduction, more than 90, I think 92% of the capacity of the new installation are lithium batteries. And the sodium-based lead acid, all those things are relatively early stage when, say 5-10 years earlier, when the lithium-ion batteries cost is higher. So right now, lithium-ion battery definitely is the dominant technology. So I don't need to I put here. So lithium-ion batteries, the structure actually is simple. Basically, we have a positive, a negative electrode, and a lithium-ion conducting electrolyte. The electrolyte can be solid, liquid, or we call the semi-solid state. The most common anode material for lithium-ion batteries are the graphite. And there's one particular type of lithium-ion batteries, or we call it the chemistry mentioned in industry. For some players, it's lithium titanate basis materials. But my understanding is the cost remains high. It probably needs some more extra work. For the cathode material, the primary lithium metal oxide are nickel, manganese, and cobalt oxide. We call it NMC, and lithium iron phosphate. So this table compares the three battery systems, lithium-ion battery system, NMC and LFP. At this time, the LFP lithium iron phosphate appears to be, in particular, over the past in the past 2 or 3 years, as the more dominant adopted lithium-ion batteries for grid-scale battery storage than the NMC, the lithium nickel manganese cobalt oxide, majorly because of the cost, of course, and also the safety issues. Also, I want to also put one slide about redox flow batteries. So this battery structure is somehow different from traditional solid-state and the lithium-ion batteries, which stores release electric energy when the redox species containing 2 redox couples flow through an anode and a cathode reactors separated by the membrane. One interesting feature, a good feature here for flow battery is the energy capacity of flow battery depends really on the size of the electrolyte tanks, and the power depends on the size of the battery. So what really are the battery R&D needs? So my focus really today is about the lithium-ion batteries R&D needs. This plot shows the, just about 1 year ago, summary of the research. This is not industry deployment, but the research labs. The best lithium-ion battery systems right now can be obtained in the research labs. You can see for the topper part, the red dot, they are mostly the higher performance, in particular the high specific energy density battery systems are based on lithium metals. We do not have very many lithium metal based on batteries, lithium batteries in the market yet, but this tells you at least one trend. Lithium metal based batteries may be the next wave. And of course, for the lithium-ion batteries, it's not the metal-based, silicon-based anode also came into play. So for the current lithium-ion batteries technologies, there are a number of research needs. For example, I just list a few of them. For battery cathode, reduction of cobalt and nickel content, expect the resource constraint for cobalt, and the battery less stable with more nickel, also the constraint of the resource, makes the researchers and also industry to try to find alternative with less or no cobalt and nickel. A stable cathode at high voltage, new cathode materials. For example, I put one example is the disordered rock salt materials. This is for the cathode. For anode, silicon or silicon carbon composite anode has been one of the most prominently researched anode materials. Lithium titanate anode optimization, reducing the cost by doping, for example, increase energy density, etc. For the electrolyte, stable high voltage electrolyte is always being expected and desired, and stable electrolyte for high temperature operation, in particular higher than, for example, 70 degrees C. This is very important for lithium-ion batteries to be operate normally in the Mideastern GCC region. High temperature electrolyte. For lithium-ion batteries, why do we have not seen very many EV cars here? Partially because of the temperature issue. So for the batteries, temperature issue, and then core is the electrolyte, which can sustain operate normally for the over 70 degrees C. And the redox flow batteries, one of our previous speakers mentioned their new innovation. So the flow battery membrane with lower resistance, reduced leakage, and longer life is the one of the research R&D needs. And also, of course, new redox chemistry. And you have seen the organic redox materials. I prepared that before I know you are talking about this topic. And there's some alternative technologies rather than the currently deployed lithium-ion batteries, and also to the smaller content, the flow batteries. One is the all-state and lithium metal batteries, which would give us a higher energy density, faster charging, and of course safe devices or systems. And the solid-state battery chemistry with higher energy density, in particular with lithium metal anode. Some research also use silicon-based anode, control of electrolyte stability, stable solid-state electrolyte at high voltage cycling, solid-state electrolyte manufacturing technologies, because large-scale manufacturing of solid-state lithium metal batteries is different from current-day the lithium-ion battery manufacturings. The second alternative technology is lithium-sulfur batteries, which also provides high energy density, in particular lower cost, because here we have sulfur. New electrolyte for lithium-sulfur chemistry, including solid-state electrolyte, and optimized lithium anode and sulfur cathode compositions to prevent, for example, migration of the lithium polysulfide, reduce the self-discharge, and increase cycle lifetime. Those are the required research in order for this technology to be really useful. The next one is the lithium air battery. It would give a very high, theoretically the highest energy density, but the technology is not ready yet. For example, new electrolyte for lithium air batteries, we need the electrolyte and the keeping lithium anode stable, preventing from reaction with oxygen, and also optimize the cathode, very important cathode material, with added addition of catalyst and control the pore structure. And here are just two examples of our own research. Just quickly, we are working on lithium metal batteries. In this case, we, in order to optimize the lithium, the electrode, we develop a one-step process using the carbon fluoride to make the anode structure more stable. The second is a recycle. We have been successfully used recycled the hard carbon to make lithium-ion batteries. So over the next maybe 5 to 10 years, there's a tremendous amount of retired batteries from EV industry. So how are these recycled batteries be used or reused for the energy storage for the power grid? Technically feasible, but economically, for me, I would put a question mark. May or may not be. There needs to be more research in that space. And to summary, only two slides. We have seen, I don't need to read all these things, we have seen the new market for grid-scale energy storage is dominated by lithium-ion batteries and, to the small extent, redox flow batteries, in particular for long-duration energy storage. And the plot here shows the price reduction over the past 10 years up to 2020. For 2021, there's a small reduction, about 6% reduction. The reduction speed is lowered, partially due to the reset by the cost of the origin of the commodity price, like lithium. And we see that the lithium-ion batteries and also redox flow batteries are under continuous improvement. There are several emerging technologies: silicon-based, or solid-state, metal, and liquid metal technologies. We already heard one of the prominent company making the liquid metal technologies. So in the next 5-10 years, if you ask me to bet, I would say that lithium-ion batteries, redox flow batteries, and potentially a few of their emerging alternatives are likely to remain the dominant energy technology for the power grid industry. And this is all I would like to give you introduction. Thank you.
All right, thank you, Dr. Mao. Actually, we can leave that wherever you'd like.
Okay.
Fine. So we have some time now for question and answer. If you'd like, maybe we can put the big QR code. We've had a few questions come in so far, but before we get to those, I actually have one question I'd like to ask all of the panelists to respond to. So, of course, we see the PowerPoint and all the technologies look awesome, and why don't we just deploy them all, and why aren't they, abundant, right? I mean, clearly there have been some issues that we're not out there right now. So my question for each of you is, what has taken the time to develop with each of your technology? What has been, one of the most, or one or two of the most challenging things about getting each of these technologies to where we are today at the verge of commercialization? What have you had to work through, go back to the drawing board on? And for Dr. Mao, you can choose one of the technologies that you were describing. So maybe we'll just go in order, and we'll start with Adam.
So let me give first some context about the battery industry. Forget about the chemistry or any particular one first. So if you're going to develop a 4-hour battery system and you want it to last 10,000 cycles, then you can do that math. 4-hour charge, 4-hour discharge, 8 hours, 3 times per day maximum. If you want to prove that you get a battery chemistry that lasts 10,000 cycles, you can't do that in less than 9 years. That's how long the test takes to run that. So rechargeable batteries, notoriously slow developing technology for that reason. It takes a very long time to prove that you've got, and that's still in a lab, right? It's still not the same as real life. As you referred to earlier, none of the lithium-ion batteries have proven they can get to 20 years either. They haven't existed for 20 years. In the context of that, you can do some things to accelerate it. You can raise the temperature, which theoretically exacerbates the conditions. Or in our case, we run it in a 1-hour charge, 1-hour discharge, and get it done in about 3 years. It's still, we're getting results today from stuff that we did 3 years ago. Now, but specifically to our chemistry and this industry, the hardest thing to do has been deal with the environment in which lithium-ion pricing has dropped by 90% in the last 10 years. So 10 years ago, EPRI targeted a battery chemistry that had an outcome of about $300 per kilowatt hour cost. At the time, that was about 1/10 the price of lithium-ion. Sounded like a great business model, but 10 years into it, they realized that lithium-ion was going to go below that number, and therefore that chemistry was no longer viable. So EPRI went back to the drawing board, just as you said, in 2016, and selected another chemistry out of MIT, and not really started again because it wasn't a dramatic change, but a change that resulted in this chemistry. So that was 5 years ago, and as I said, in the context of it takes 3 years at least to do testing, that's the reality of developing batteries in the world.
So you're being chased by a bear, and the bear is moving faster and faster, so you have to
right.
hide for a little bit and then come out twice as fast.
Right. But in 22, lithium-ion prices have actually gone up as a result of supply chain issues. It's hard to know whether that's going to be sustained or not, but for now it does look like it is. So that's creating a bigger gap. So that's nice for us.
Thank you. Dr. Kravchuk?
Yes, so the short answer is quite the same. It's the low-cost battery, what took that time. And the long answer is we started with a completely new technology. So the challenge was to have this organic material running and to have low-cost material. And on the way, we learned, the first thought was we can buy everything else. We can buy the stacks, we can buy the battery management system, but the battery world is not that major that you can do this. And the organic material has other requirements than the vanadium flow battery. So we learned a lot what we have to do on ourselves, and the result is the whole product. And to have the costs really low and to have a mass production, this was what took really time.
Great, thank you.
Maybe we're a little bit of an outlier because it didn't take all that long. The company is only 2 years old. The feed design was validated by Fichtner in the summer of 2020. The rotating equipment was ordered a month later. The project is nearly completed construction, so less than 2 years from company foundation to commercial operation. I don't think it is all that long. For us, the long lead item today is the compressor, because the supply chain is not used to making these compressors. But as we ramp up, we think we'll have a time from notice to proceed to COD of about 12 months. 2 years from scratch, I think that's not so bad.
So I guess that leads me to a related question, which is what about the Energy Dome system is unique and novel? Is it's the cycle itself, or the order of operations that you've chosen to go through? Because if everything's off the shelf, then I mean, what is the?
The only thing is, like I explained on the earlier page, is that people have been working with compressed air and liquid air, and air is not a very good liquid working fluid for storing energy, because either it doesn't go liquid, you have a low energy density, large volume, or it does go liquid and you have a low RTE and a high capex. So you replace the air by the CO2, that's the brainwave. The process is patented, but we've not invented anything new. So it's maybe not fair, it's a bit of a shortcut, it's maybe not that impressive, but I think it's actually pretty impressive to go from standstill to commercial in under 2 years.
Yeah.
But it is patented, so if you all think it's a great idea and you can do it in your backyard, unfortunately you can't, because the process is ours.
Thank you. Dr. Mao, have you thought of a technology you want
for lithium, I like to, in general, to describe the development of lithium-ion batteries. Really, it is traditional materials discovery innovation to reach today's status, that really low-cost lithium-ion batteries. We need, in general, we need a breakthrough, for example, lithium and the iron phosphate type of battery system is a breakthrough, the discovery of the new chemistry. And based on that breakthrough, then the incremental growth of the improvement of technologies and the lower cost. And for the next step, I think I mentioned in particular the silicon-based anode technologies and the lithium metal-based, and also in combination with solid-state or solid-state electrolyte, solid-state battery, are the two technologies I would say, to be conservative, that those are two technologies to watch. Why I say that one? Actually, there has been a report in terms of investment. Last year, 2021, there are over $2 billion investment in the space, or we call the subspace, of anode technology, in particular silicon-based technologies. And there are a bit more than $2.8 billion invested in, also last year, in lithium metal and solid-state electrolyte-based battery technologies. So from the investment quantity, you can see that these two technologies are, I just mentioned, are the technologies in the near term to watch. I would say that impossible for these two technologies to be implemented in the field in the next maybe 2-3 years, not yet, but in terms of midterm, say 5 to 10 years, it's quite possible one of these technologies are going to be replacing, at least to be coexistence with the current day lithium-ion based technology, in particular FEV technologies.
Right, thank you. Were there any questions in the audience at this point in time? Yes, we have 1 and 2 over here. Or 1 and 2 that way. We'll get you the next one.
I can go first. Hi. Giriraj Rathore from Wärtsilä Energy. My question was related to the response time. With lithium-ion batteries, I think that's one of the distinguishing features, that they have faster response time. So for you, Doctor, solid flow batteries and Energy Dome batteries, what is the kind of response time that can be expected from these kind of batteries, especially for shorter duration microcycling kind of applications? Thank you.
So maybe I start. Yes, the solid flow battery is always running, so the pumps are always running. So you have a very, very fast response. So the limiting point is always the power electronics, and this depends on the application.
Well, in the case of Energy Dome, the CO2 battery, it has been designed specifically for daily cycling. So we've not designed it for response time. Of course, when the system is running, either compressing or discharging, we have inertia with rotating equipment, then we can actually respond quite quickly. From standstill to full load, you're talking minutes. So it is not for fast response, it is for energy shifting.
Thank you. There's a question up here in front.
Yes, this is Bender Al-Merri from GCCIA. I would like to thank all panelists. This morning, Mr. Gabe, in his presentation, he stated that the energy storage could or can provide the ancillary services, but when the storage battery are sufficiently charged, and the sufficiency could be anything from 70%, 80%, up to 100. So my question to you as technology developers, when we can depend on the energy storage to provide the ancillary services?
So the question is when we can rely on energy storage
Exactly,
to provide,
yeah.
or like under what conditions, or whether or not it can do it now?
No, like when we inject from the battery storage to our system,
Mm-hmm.
like how that will help us to provide the ancillary services.
Well, I'll just say at a high level, and I'll allow some of the technology developers to provide some input as well. There are, storage systems that are providing ancillary services now, the lithium battery systems, as well as pumped hydro systems providing, frequency regulation, spinning reserve, and, in some cases even frequency responsive reserves with very short durations. Some technologies, and I think related to what we just heard in the previous question with response time, some technologies may not respond instantaneously if they're in a standby state, or like a cold state, and so they may have some limitations about when they can provide ancillary services, and which ones to what degree can be provided. I don't know if would any of the technology vendors like to provide
I'd like to add a long duration energy storage kind of twist on that, because the world will change when you've got long duration energy storage. So just to put it in context, ancillary services were the reason that batteries became grid storage. The fast-acting aspect of it made it a much better grid balancing mechanism than anything that previously existed. And to the extent at which early markets like PGM in the United States and FFR in the UK saturated from batteries much more quickly than they thought would happen, because the batteries were so fast-acting that it basically served the purpose. So now we need energy shifting. And if you look at forecasts from Bloomberg or IHS, S&P, those kind of companies, the percentage of energy storage in the future that's energy shifting is like 80%. It's the killer application. But long duration energy storage can do ancillary services at the exact same time. If you are shifting 4 hours or 8 hours of energy from the middle of the day to the evening, you can superimpose on top of that an ancillary service. It could be frequency response, it could be any of those things, because it's got the capacity in order to handle perturbations of state of charge all day long. And so that's stacking business models, stacking ancillary services on top of the value of energy shifting is the reason that energy storage becomes a value in the market. And so you need a technology that can do all those things that actually makes it work economically.
Yeah, no, that's a good comment, and I'll answer a question that I read in the poll everywhere, because I think it's related. So this is a question I think that was directed toward me, which is, it seems there should be a role for short duration energy storage in 100% renewable energy scenario. Why does the study indicate no need for short duration? I'll start by saying that these models, like the results I was presenting earlier, very complicated economy-wide model, so it's hard to say one thing because of this, then that. But as a general point here, as you get longer and longer duration energy storage, this storage can provide all of the shorter duration services that Adam was just talking about. The efficiency will come into play, to the extent that you have low efficiency systems, like, you might not want to operate those preferentially. But having said that, once these long duration storage exists, like, they can easily come back and eat up all of those short duration services once it's been justified to deploy them. Are there any other questions in the audience at this point? Up in the back here.
So I'm Harish Kamath from EPRI. I've been working in energy storage for a long time. So thank you very much for presenting your technologies, great new concepts. I've seen a lot of concepts, good ones, not quite succeed along the way. And a lot of that is not about the capabilities of the technology. It's about being able to get credibility relative to the options that are already on the market. And I just want to point out, maybe a little pointedly here, but and my apologies for that, but I want to point out that you're going to have trouble making your technologies viable relative to lithium ion if you have not tested them in the field to any significant degree. And I'd like to understand what your plans are for pilot projects, for large-scale pilots or demonstration projects in the near term to establish that, and whether you would be interested or open to developing demonstrations here in the Gulf countries.
Thanks, Harish. Appreciate that question. Maybe we can, if you don't mind, we can just go down the line if you want to make a few comments.
Right, 100% agree with that. Our plan is we've got our first demonstration system is going to be done with a large data center in a couple of weeks. We start that, and then we have a plan for about 5 or 6 pilot systems in 23, and we are actively negotiating with people who want to place those. EPRI is one of those partners who would be involved with a utility who wants to do that in the United States. We do have a Middle East partner here who is interested in a pilot system here. We very much want to put that in place, because you're 100% right. Unless people can see it and touch it and analyze the data, then they're not going to trust it. You've probably all heard the expression, there's liars, damn liars, and battery suppliers. So, it's a tough context in which to bring a new technology forward. Completely agree with the comment.
Thanks.
Okay, so thank you for the question. You're completely right, and these are the next steps we are going. We start in Germany with smaller prototypes in the range of 1 to 5 megawatts, and we plan international prototypes, demonstrators in the field, and of course there's interest for new areas for the demonstrators.
The case of energy domain is a little bit different. The processes itself are well understood, the components are well understood. We have lab tested the thermal energy store, so all the components work. So we've gone straight to commercial scale, 2.5 megawatt, 4 megawatt hours. But when it goes to commercial, we're looking at 10 megawatt, 10 hours, 20 megawatt, 10 hours. We sold our first 10 megawatt, 10 hour system. We're negotiating a couple of 20 megawatt, 10 hour systems. There seems to be little doubt that it will work. But yes, any inquiries from would-be partners or would-be customers to build a 20 megawatt, 10 hour system in the region would be extremely welcome. We're working a couple of leads. It ain't over till the fat lady sings, as they say. I didn't know that expression about them liars and battery suppliers. Open to discussions. Thank you.
And Dr. Mao, I know it's a little bit of round peg in a square hole for you, but could you make any comments about the R&D work that you're doing and how it comes to be demonstrated in more field-ready applications?
Yes, I mentioned earlier that 2 years ago I came here to lead the Mars Institute. So Mars Institute was founded 15 years ago in Abu Dhabi with the objective as the research, R&D, and development R&D hub for sustainable technology development. And let's see, this year, starting this year, January this year, we received Abu Dhabi government funding of $18 million to develop, not only develop, to research, development, and demonstration in collaboration with industry of a renewable integrated power grid, in particular, solar plus energy storage to the power grid. So in my proposal, when I came here 2 years ago, this is my, the largest proposal ever written. By looking at the general structure of the GCC region, GCCIA as leadership, and also the Abu Dhabi and the UAE, I commented in my proposal that the GCC region, in particular the UAE, has a perfect structure, power grid structure, to demonstrate the new technology, implement new technologies in the region. In particular, I've been working closely with EPRI over the past almost 2 years under EPRI's direction and also leadership in the technology directions. I think that we are able to implement the best available technologies of the world, bring them here, we implement into our power grid, and to show the world that, yes, GCC region, we have this, the structure, and we have this successful demonstration can be exported to other regions. So this is the thing that we are pushing very hard to the growth of Mars Institute itself, not only fundamental research. Really, we do not do fundamental research in our institute, but applied research, technology development, we call it transformative technologies leading to adoption by the industry.
Excellent. Well, I think we're out of time for this session for today, and so I just would like to thank you all and ask all of you to join me in thanking our panelists for this session.
Thank you.
Thank you, Ben. Thanks to all our speakers for today. Now I would like to ask Dr. Arshad Mansour, CEO of EPRI, to present trophies to the speakers. Ben Khan, Program Manager of Energy Storage, EPRI. Adam Briggs, CEO of EPRI. Dr. Nastaran Kravchik, Chief Technology Officer, CM Blue. Rembrandt Neeson, CEO, Energy Dome. Professor Samuel Mao, Senior Director of Masdar Institute of Khalifa University. And now we would like to take a group photo. Now I would like to ask Dr. Arshad Mansour, CEO of EPRI, for his closing speech.
Thank you, thank you. It's been, I think, 3 days of, when I came on the first day, we said, we are crawling now. I think we got enough material to start walking. And walk we will. But I really want to thank, I know GCCIA and EPRI, all our staff just did an excellent job, but all the speakers and all of you attendees who took time from your very, very busy schedule to come means that you're serious about energy storage. And I think we will see an inflection point of energy storage deployment in this region. And 5 years from now, we'll look back at this event, that this event was a catalyst. So going back to where I started, I think what is the takeaway? I'm assuming you will get all the slides and all the materials, but really the takeaway is you heard about projects going on even in the Gulf region, but nobody knows about it. So I said that we need top 10. We need to identify top 10 technologies that are at early stage or that are stages that we can actually deploy. And some of them you saw it over here. And let's start working with GCCIA. Their focus is collaboration. Our focus is collaboration. Collaboration because at this early stage, even it's a mature technology, lithium ion, 8 hours. But still the application of it for a future power system, we need to learn from each other. We need to design the experiments the right way. We need to collect the data in an independent way to see how these technologies can be scaled up. So I'll go back to let's use this forum as a starting point for a top 10 deployment of technologies at scale throughout the Gulf region. Let's GCCIA coordinate that activity. And even though we may not, the economic sense, the cost-benefit analysis may not work right now because you're anticipating a future, but I think that would be a great outcome from this session is, get the Gulf region ready for energy storage, both 4 to 8 hours and longer duration. So once again, thank you to all of you. Engineer Ahmed, do you want to say a few words to close? Because you, at GCCIA, we're just thrilled with the partnership. It took some time for us to be a partner, but I think we are now also, we are from a GCCIA and EPRI perspective, we will be running, not even walking. So thank you so much.
Now we would like to ask His Excellency Engineer Ahmed Al Ibrahim, CEO of GCCIA, for his closing speech.
Wow, 3 exciting days, I think. When we came here, I think all of us had anticipation. What are we going to listen to? But I think all of us were amazed by the kind of subjects and the kind of knowledge that we got. I think all of us have some takeaways, and it will all depend where we come from and what's our background. But let me maybe share with you some of my takeaways that I had. We all, I think, learn about the importance of energy storage and the kind of transition that's happening. We all learned that we need a full spectrum of energy storage and how to implement it in our systems, ranging from short-term operational ancillary services going to long-term for adequacy requirement. And this is all needed for our future power systems. I think we learned about innovation, that we need innovation to reach the net zero targets that we all have. And I think this last session we've seen the emerging technologies for batteries that can be part of the innovation that we need to reach to that stage. I think one important part is the need for the GCC roadmap to develop towards this energy storage requirement, and the need to also integrate this process into our planning I think members of our planning committees have been here today, and they're having a meeting tomorrow. So I hope the takeaways are discussed in these meetings, and this kind of roadmap is integrated into our process. And this is what we need. We've seen initiatives from different countries, and frankly, initiatives that we didn't hear about before, like from Saudi Arabia and other places. These kind of initiatives, we need to learn about it, and we need to have the lesson learned in a holistic and a cumulative process, not only individually. I think our efforts in the GCC needs to be harmonized, not randomized, and put in the right path along our roadmap. So thank you all for here, and I'd like to extend my appreciation to our chairman and the board of GCCIA for supporting us in these kind of events. During Expo 2020, we had a few events starting from October, and we have a big team working on these events. And I think this might be the crown of these events, and it's a nice closing for our participation in Expo 2020. So again, I'd like to thank Dr. Arshad for his leadership in EPRI. We really appreciate this kind of partnership. We are starting a journey of collaboration, and I think collaboration is a key word that we need to work on. The team of EPRI are all here, and I'd like to appreciate their participation in leading this. Also, I'd like to thank the distinguished group of experts that have really given us the knowledge and the expertise and shared with us new viewpoints that have opened our mind on new things. So thanks to all of them for their participation and for the technical content. Of course, this wouldn't have happened without our organizing teams from both the EPRI and GCCIA. So I'd like to thank all the guys from GCCIA and EPRI, especially leading that from our side, Mr. Mohammed Sheikh, the Chief Network Officer, Mr. Zaid Al-Ansari from EPRI for coordinating, and for the logistics and the organization, Dr. Ali Al-Bukhit and the PR team and all the GCCIA teams. You've done a wonderful job. You made this to such a professional level, so thank you all for making that. But last and not least, I thank all of you, the audience, for your participation. And we've seen everybody has been there since the early hours until the end of the sessions. And I think I would like to thank you all for your participation, for your excellent questions, and for being part of this event. And I hope that we will meet again, inshallah, in future events of the GCCIA. Thank you very much.
Thank you, Engineer Ahmed Al-Ibrahim, for your closing speech. Thank you, Dr. Arshad Mansour. And now we would like to move, we would like to take a group photo with all our speakers that participated in this event. On the stage, please. With all our speakers, with Dr. Naif. Thanks to all our speakers who were part of this event. And now we would like to take Now I would like to ask all GCCIA and EPRI committee organizers for a group photo. GCCIA and EPRI committee organizers, please on the stage for a group photo. Well, ladies and gentlemen, that wraps up our last day of the event. Thanks to all our GCCIA and EPRI speakers, organizers who worked on this event to make it successful. Thanks to all our attendees who participated in this event. Thank you all for being here with us. It's a pleasure to host this event, and I wish you a pleasant day.